Okay, good morning, everybody. So it's my very great pleasure to welcome you on behalf of the Department of Chemical Engineering and Biotechnology. My name is Roisin Owens. I'm Professor of Bioelectronics here. I'm also Deputy Head of Department, so I'm representing also Clemens Kaminski, Head of Department, who couldn't be here today. So probably many of you have been to this building before. It's a beautiful new building located on a very exciting campus in the heart of West Cambridge, surrounded by departments of engineering. You've seen the new physics building going up, and it's a very exciting place to be. So, as you may know, Chemical Engineering and Biotechnology was formed by the merger of the Institute of Biotechnology and the Department of Chemical Engineering in 2008. But this was the first time when the building opened that the two departments were co-located. A brand new building located, as I said, in the West Cambridge site. We have over 30 academic staff and 50 professional staff and large numbers of undergraduates, PhD students and postdocs that make this a very vibrant place to carry out research. We're undergoing a transition, and the merger, the chance to come into this new building, was the opportunity for us to look on our strengths, to see where we have core expertise, and you can see those listed here. I unfortunately didn't know John Davidson very well. I came in 2017, so only met him very, very briefly. But he's embedded in the DNA of this building. You can't possibly not realize how important he was to this department. One of the last times I saw him, he was sitting with some Part 2B students, helping them to work on their research project. He was a big believer, from what I've heard, in the merger and in the movement of chemical engineering and biotechnology together in the future. And I hope you'll have a chance to look at our new rebranded website and see that we have some key areas we're moving towards. As a biotechnologist, I'm of course pleased that some of those are in the healthcare area, but of course we have to be aware of the sustainability goals and thinking about new ways to think about energy and other major problems that face us at the moment. And we've been thinking about some key areas such as renewable energy, and of course, later on you're going to hear from some of our current academics and the research they're doing towards this goal, and also in things like treating an aging population. So I hope you'll enjoy the day and you'll understand how John Davidson's legacy is still alive in the work we're doing today, and understanding how we can be involved in facing or in solving some of the world's biggest challenges. We're at a very exciting juncture in our history too, because we're about to launch a new tripos. So we will no longer be chemical engineering tripos, we will be chemical engineering and biotechnology tripos. This will be a 4-year degree where we admit the students from the beginning, no more fighting with the natural scientists and the engineers for their students, and we'll admit them in, and they will be taught from the get-go the core underlying principles that they will need to tackle some of the challenges I alluded to. If you get a chance, have a look on our website, see what the course is about. We'd love to hear your feedback. We will be admitting, so I think 16th of October is something around that, is the deadline for application. So do encourage young people, young bright things you might know, to apply to our course, and it'll be a very interesting time. And again, as I said, very much in line with what I understand was John Davidson's vision for the future. Okay, so the program is quite packed. We were very keen to have some perspectives on John Davidson the person, as well as John Davidson the scientist, and then leading into the afternoon session, which is more about what's happening in the department today. Unfortunately, we're still not COVID-free, and we've had a couple of cancellations last minute. Professor Seville was very sad not to be able to make it, and unfortunately was not well enough to be able to record a contribution. Professor Darton was also struck down. He thankfully was feeling well enough that we were able to record his presentation. And you know, the beauty of technology means that we also have a presentation from Professor Clift all the way from Vancouver. So that session will have some live and some online. I should mention also that today's proceedings are being recorded, so there will be an opportunity to catch those, or maybe for some people that you're aware of that couldn't make it today, they'll be able to access that material later. The afternoon session, we will introduce it in just after lunch. There will be one change there too, but I would like to confirm it first. Okay, so now to housekeeping. So there are 2 emergency exits, and the assembly point, if there were to be a fire, there's no planned fire drill today, so if you hear the fire alarm, it's real. The assembly point is past reception, where you came in the car park. There's one of those green signs, so that's where you should head to. If the fire alarm were to happen during one of the lunch or coffee breaks, the assembly point is out on the terrace past the tea room. But there will be people directing you there, probably me in a high-vis jacket. There are volunteers today, students and postdocs, who are wearing a heart valve t-shirt. You probably saw them at the reception. If you have any questions, please ask them. We're very proud of our new building, and you will have an opportunity to tour it if you should wish to do so. There were sign-in sheets at reception, but you can still sign up in the coffee break if you'd like to do so. I encourage you to go and see the lab space. It's really very interesting. Okay, I would like to make a very big thank you to Elena for all of her work in organising today. It just really would not have happened. And of course to Rob and Ansel for all of the AV support. I really couldn't have done it without them, so thank you to them. Also to the Scientific Organisation Committee and to the department for sponsoring today's event. Okay, I think I've said everything I need to say. And my next job is a very pleasant one. I'm going to introduce our first speaker, who is Professor Sir David Harrison. He studied natural sciences at Selwyn and then received a PhD in physical chemistry. And he taught, he was a lecturer in this department from 56 to 79, and then went on to have a very illustrious career as Vice-Chancellor first of Kiel and then Exeter. Outside academia, he was chairman of the government's advisory committee on the safety of nuclear installations and was elected a fellow of the Royal Academy of Engineering in 1987. He co-authored a book with John Davidson. They had carried out pioneering work on fluidization, and they summarized some of their work in a book on fluidized particles in 1963. It's a very great pleasure to have you, and the stage is yours. Thank you very much.
Thank you. What is that? Oh, I have a little. Set up. Yeah. Well, thank you very much. It's both an honor and a great pleasure to have this chance at this celebration for the life and work of John Davidson. I knew him really for 60 years, and for me, he was a close colleague and a dear friend and a godfather to my daughter. John joined the department in 1952, 4 years before I did, and we were both recruited by the first shell, Professor Terence Fox, who was needing to replace some of the original staff members who were moving on to other things, people like Peter Dankwitz, whose bust was unveiled here quite recently. And Fox was looking for recruits from the old mechanical sciences tripos on the one hand, or the natural sciences tripos on the other. And he was quite blatant about it. He said, if you join my staff, you're going to learn to be chemical engineers by teaching it, which is precisely what he'd done. So that was his stance. But it certainly meant that there was a strong emphasis on teaching, but there was a project positioned in the fourth year, which John made an extraordinarily useful vehicle and used it to an extraordinary degree. This led him to, for example, to study the gas bubbles in liquids, spherical when small, spherical capped when large. The original work on the large bubbles was done by Sir Geoffrey Taylor during the Second World War, then to better understand what happened when you exploded a depth charge. You got a large bubble. But John moved into exploring the possibility that these moving bubbles would give us an insight into fluidization. His marvelously elegant work was followed up and indeed confirmed by X-ray work carried out at Harwell by Peter Rowe and his co-workers. And we gathered together a range of publications from 7 graduate students, indeed in total at the time, into the book which has been kindly mentioned, Fluidized Particles. I shall never forget the day the manuscript went to the Cambridge University Press, because it was just 1 week before I was married. It was a close-run thing. But the book came out, and we, of course, pleased, needless to say, it was well received. And we noted also the difference a book's impact has as opposed to or alongside research papers. The book was immediately translated into Russian. There weren't any royalties, I'm afraid, none whatsoever. But it did lead in 1966 to an invitation from the Soviet Academy of Sciences to visit the Soviet Union as it then was, and in particular Moscow and Leningrad as it then was. What it proved impossible to do was to find out anything in advance of what this would involve, except it was going to be 2 weeks. We couldn't answer questions that were being constantly posed by our wives. And anyway, on our very first night in Moscow, a handwritten piece of paper appeared after dinner, literally handwritten, with the itinerary for 16 days, and which they went through. It was very attractive, because not only did it include visits to universities and research establishments, it included visits to stately homes and the Bolshoi. And then they said to us, have we missed anything out? And we thought this question had some substance. But then it became very clear when we mentioned that we had correspondence with people in Minsk. Then Minsk was a very long way away. And in fact, the handwritten itinerary was set in concrete. It was, and we very quickly expressed our appreciation and got on with it. But when we got to Leningrad and gave lectures there, the Minsk people were in the audience. Now there's a commander. Well, it perhaps hasn't changed. I would like just to touch on one thing John did, as it were, outside Cambridge, to give just an insight into the range of his work. On the 1st of June 1974, there was a dreadful explosion in Flixborough in Lincolnshire, killing 28 people and injuring another 36. And the Department of Employment instantly set up a court of inquiry. Michael Foot was the minister at the time. And very soon, John got this phone call asking him to be an expert witness. Being the careful man that he was, he felt he ought to mention that, though it was June, he was actually going to Australia on sabbatical leave in January 1975. And they said, no problem, Professor Davidson, no problem at all. This will be over long, long before that. Not so, not so. 70 days of hearing and the sabbatical leave got pushed back. Now, just one more area, really, and that is we did have the great privilege of visits overseas, not together, not least to the United States and Canada. And when we went there, Suzanne always provided John with a shopping list, which he found quite difficult to handle amongst what he was supposed to be doing. But anyway, the one I want to particularly mention was the visit we made in 1970 to Australia, when John was president of the ICME, and this great conference was divided, needless to say, between Melbourne and Sydney. But this was in Melbourne, and we were sitting together listening to a presentation from a British university about droplets from an atomizer falling down, and the experimentation looked pretty tidy. Anyway, I noticed that John was sort of fiddling with a piece of graph paper alongside me while this was going on. And anyway, when we got to the discussion, he joined it. And of course, being very, very courteous in every sense, he complimented the workers on their experimental work, which indeed was good. But they'd made awfully heavy weather at an elaborate correlation to explain in some way or another what was going on. And he then went on to say that actually the results could just as readily be handled by Newton's laws of motion. And they might care to look at the graph paper he just prepared and consider it. It was very much John at his intellectual best and helpful best. Now, I've touched on only the first 20 years of his life as it were, as an active chemical engineer, a remarkable life, because that's what I remember. That's what I remember very, very well. But of course, there are another 40 years to go, and that's really the subject of this day, this special day. Thank you very much indeed.
To ask a question of Sir David about his time with John, if you move on. Anybody wanted to question about Newton's
Don't you dare.
There's one. Okay, hold on. I'm going to come up with the microphone.
I can shout.
You can shout.
I can shout. As I said to you earlier, you were my tutor in the mid-1970s because there weren't any chemical engineers in my college, which was fortunate because I then got them taught by you. You mentioned that John Davidson, when you were in Australia, did this bit of graph paper and handed it over. When I did my research project, he did exactly the same thing with me. He gave me a piece of paper in his quiet, understated way. He said, Michael, I think this might help you. And I've still got the bit of paper. I was looking for it to come here, but I couldn't find it. But he had succinctly, in one piece of paper, pinned down what I had been grappling with for the best part of half a year. And I thought this was a unique intervention on my part. I now learn he obviously did it quite often. Is that true? Did he often slip quietly little bits of paper to underperforming students?
Well, I think the answer is yes. I mean, I think he had certainly a supply of paper, and he was aching to use it. I mean, because he was basically sparked off by your problem, and he was certainly sparked off by that problem in Melbourne. And it's all right. I've got something I can contribute here, and that's what he did. A marvelous gift. And also the principle of not making things more complicated than they might be.
Thank you.
Thank you very much. So our next speaker, very pleased to have John Davidson's daughter, but also somebody who had a very illustrious career. She worked as a government lawyer for nearly 40 years in different government departments. She was Director of Legal Services in the Department for Culture, Media and Sport, the Foreign Office, Department of Work and Pensions, Health and MOD. And she retired from there in March this year. She worked on many different areas covering restitution of objects looted in World War II, counter-terrorism, universal credit, the reorganization of the health service, and lastly, the war in Ukraine while at MOD. We're very pleased to have Isabel Letwin, who's going to give us, I think, more about John Davidson, the person, the father. So over to you. Can I just check, can everybody hear at the back using the microphone that we have now, or do we need additional? A little bit higher, because maybe we'll just angle this a little bit closer.
Brilliant.
You want to do a sound check?
Can you hear me? Is that all right? Up a bit?
A little bit. We can also put a mic on you if that would be better. How do we do that?
Try that.
Is that any good? Or
Same.
still need a bit
How
more?
about this? So you tell me where you want that. Is it turned on? I don't know if it's turned on.
Oh.
Is that on?
Excuse me.
Sorry about this.
That's quite right.
See what you're doing with the original video?
No, it is. It's
It is?
very subtle.
Okay.
Right,
Oh,
it's
okay.
fine.
Do you have a pocket? Or
I'll just hold it.
you do?
That's fine.
Okay.
Yeah,
Oh.
that's great. Thanks. Can you hear me now? Is that all right? Yeah. Okay. Jolly good. Oh, thank you so much. That's great. Terrific.
To turn the lights down.
Shall I just check? Wait a minute. Yeah, great. Okay. So, yes, JFD, life beyond the bubbles, at home, etc. Much of the symposium is focused on my father in chemical engineering, and I'm going to give a brief bird's eye view of what he was like outside the lab. He was born and brought up in Newcastle around the time of the Great Depression. He used to talk about the oddity and sadness of men standing around on street corners chatting because they had no work. His father died when he was 9, and his mother then supported the family household by teaching. The household included a sister and a housekeeper, as well as John and his mother. He used to mention that other widows with no such qualifications had to take in boarders as the only means of supporting their families. Perhaps partly as a result of this, he never had any of the hesitancies of some of his generation about the intellectual abilities of women, nor about them working, and indeed he took a great interest in and encouraging interest in my working life and in advancing the cause of able female students and colleagues. During World War II, he was evacuated to the Lake District, a huge contrast to the sootiness of Newcastle. This may have helped to form his love of walking in beautiful hills. He and my mother would go on alpine holidays each year with us all. I'll show you a photo of that. Yeah, there we are. Minus me, just my brother, I think I took the photo. Although there was some difficulty about getting my mother to walk very far uphill. Unlike him, she was not built for sporty activities, and her upbringing in urban Berlin had not endowed her with the slightest hint of a sporting disposition. My father would patiently and incongruously carry her handbag, which she insisted on bringing with her on the alpine pastures, but found rather heavy. Indeed, early in their married life, he had to carry her rather than merely her handbag over a mountain pass, a consequence of mistakenly arranging a taxing climb from mountain hut to mountain hut. And I'll show you, he was pretty energetic in mountains. There's a photo of him looking rather sporty in the Alps, on very, very high up, I think. His arrival at Trinity in 1944 opened the door to a new world, which he loved from the time he entered it until the time he departed this earth. You can see he looks very happy in Neville's Court there, when he was probably in his 90s, I think. For nearly 70 years as research fellow, steward, professorial fellow, vice master and life fellow, his life was intertwined with the life of the college, as it was also with the life of the Department of Chemical Engineering, which he joined at the start of his teaching career, as you've heard, and to which he cycled almost to his dying day before it moved to this place where he did come during his last year of his life. As a child, I often visited him, both in his college rooms and in his room at the department, where I drew pictures on the blackboard, carefully retained by him until they had to be rubbed out for the next supervision. Although not at all clubbable, being diffident, modest and sensitive, he was nevertheless very happy in these two different institutions and, in his understated way, but with quiet force of character, he exerted considerable influence. His delicacy of manner concealed an acute emotional intelligence, as well as a considerable degree of shrewdness and intellectual tact, qualities which he was more than willing to deploy in order to win round potential opponents in order to get things done. He often said to me, "A soft answer turneth away wrath," from the Proverbs. When I remarked to him once, rather worriedly, that I didn't say very much in meetings at work, he replied that he never said anything in meetings unless he had something important to say, but that perhaps this inclined people to listen more carefully when you did say something. Part of the charm of his manner lay in his puckish and subtle sense of humour. No doubt this helped him navigate smoothly some of the difficulties inevitably arising in the two institutions at the core of his life, and also in the national institutions, in whose management he participated at various times. I remember a Trinity fellow who wrote to him complaining that my father's actions in a particular case had been, quotes, contemptible. He received, by way of response, the observation that the old contemptibles had been rather an admired expeditionary force. On another occasion, when as steward at Trinity, he wrote in gentle terms to a young fellow that T-shirts should not be worn at high table for dinner, he was very pleased to discover that his mildly jocular letter had been framed and was hanging on the wall of the fellow's rooms. He was very good at explaining things, and particularly good at explaining maths and science to the young, i.e. me, in a clear way. Whenever I had maths or science homework, the phone would start to ring in the evening, with the rest of the class wanting to find out how he had explained the problems. And this same clarity of thought and elegance of expression was apparent in whatever he wrote, in his letters and speeches as much as in his lectures and scientific papers. He never believed in a science divorced from either practical life or literary style. He was often to be found late at night editing the papers of his students to make them clearer and more elegant. His engineering interests extended to the domestic sphere, and he was extremely, albeit in his customary way, unobtrusively active in this. I have many childhood memories of him either working at the table in our sitting room, where he drew rather beautiful diagrams which I liked to inspect, or mending things at his workbench in the garage. When my Girton friends arrived at the house, they would find on leaving that he had pumped up their bicycle tyres or mended things he thought were awry. Frequently, some of the weekend was spent in a boiler suit with his head under the bonnet of the family car, a Morris Minor, which, due to his careful attentions, lasted for 26 years, and in which the whole family would travel on alpine holidays. Or, at weekends, he was invisible, with only his long legs to be seen protruding from underneath the car. Safety, possibly born of his experiences in the lab, was always an important consideration. Got a photo. Here he is, mowing the lawn in a hard hat. He would arrange wonderful and carefully organised firework parties for our children, ensuring that each child at the party had a pair of safety glasses taken from a big tin which he kept for the purpose. I don't think I've got that tin anymore. He would always ask me before coming to stay with us whether there was anything that needed mending. This was a godsend to us, both working full-time and with small children. I'll show you. Here he is in his boiler suit at the age of 91, still mending things for us in Dorset. When we had 2-month-old twins, we misguidedly took a landmark trust house in the Lake District, which we were horrified to discover had no washing machine. We brought with us on the roof of our car an old-fashioned, non-automatic, I say this word advisedly, washing machine lent by a neighbour to see us through the holiday. My father was delighted by and interested in its lack of automation, and, as a lifelong insomniac who didn't need much sleep, washed baby paraphernalia throughout the night, guiding the machine through its different stages. Being awake in the very early hours, and also brilliant with children, he helped me bottle feed the twins who were waking sequentially, she says bitterly, throughout the night. I've got a photo of him. Here he is on that rather exhausting holiday carrying one of the twins, 2 months old, I think. While shy, undemonstrative and reserved, he was a deeply affectionate person, not only to his family but also to others, such as elderly Trinity fellows who were ailing and whom he would visit in hospital or at home. He viewed the world, as did my mother, with a generous heart, benign optimism and friendliness, but his shrewdness was as evident in his play as in his work. When appearing on the tennis court, despite being somewhat deceptively attired in ancient white Bermuda shorts, he had a tendency to place the ball with considerable dexterity and more than a hint of cunning. As I remember these various features of his personality in the company of those who shared his enthusiasm for chemical engineering, I'm struck above all by the continuity and integration of his life. Home life, the life of the college, and the life in the department were all part of one whole, in which the same qualities of delicacy and intelligence, clarity and shrewdness, affection and determination were applied to each activity and relationship. Perhaps it was this exceptional integration that gave him, despite his intellectual power, a peculiar air of purity and simplicity. Thanks.
How to follow that? Well, our next speaker is Peter Davidson. Peter read engineering, then chemical engineering at Cambridge, and then spent 27 years in ICI in engineering, plant and research management before undertaking startups in biofuels and improving internet access. He was senior innovation advisor in 2 government departments and is a fellow of the Royal Academy of Engineering. So we'll just get you mic'd
Can
up.
I avoid that?
Yes, if you can stay close to
I
this
will
microphone,
stay close.
please. And maybe speak up.
And if the people at the back can shout if they can't hear me, put their
Wonderful.
hands up.
And maybe you stand there. Great. You've turned it. Great. Thank you very much.
Thank you. And can I say this is a personal perspective of my father's time in chemical engineering and perhaps some of his views on the future of the subject. Before that, to thank Racine and the department for organising this symposium and for you all to come. So my father started, as David alluded to, chemical engineering in 1952, and I think it's fair to say, everybody would agree here, devoted himself to the subject and its impact. The department, its staff, its students, its assistant staff, and administration. He produced about 3 papers a year for about 65 years. Even after his death, papers were appearing. My perspective is that the last ones were at least as good as his first. We talked over about 40 years after I graduated, usually a couple of times a week, on technical problems, his, mine, managerial problems, staff issues, college and family. I've tried to summarise what I see as his approach on this slide. And I'll come back to some of those points later on. And Isabel has alluded to, we almost never saw him making a sharp comment to folk in public. I think fundamentally he had an abiding interest in how things work. He related to me how at an early stage of his youth he was fascinated with bubbles coming from when you pulled the plug out of the bathtub, and then used to run them with cold water to see what happened. I think he had an interest in the impact of ideas, not just the ideas themselves, and he had an optimistic, benign view of life and people, although it's fair to say that underneath the calm exterior he could worry. One of his greatest industrial impacts was his contribution to the Flicksborough inquiry that David has mentioned. And to remind you, it happened on a Saturday. Perhaps 500 people would have been killed. You can see on the left of this slide the main office block here, which didn't exist anymore after in the aftermath. Flicksborough led to a widespread public outcry at the time, and perhaps together with a passage of the UK Safety and Health at Work Act the same year and the HSE, it led to a more systematic approach to process safety, and I'll show you something of the impact of that. The government stepped up to the plate and commissioned a public inquiry with an extremely able team. So Michael Foote at the time was Secretary of State for Employment, and this is the Hansard record of the terms of reference and who to be appointed. When the civil servants approached my father, you've heard the comment, it'll take 6 or 8 weeks. He recorded, in fact, the court sat for 70 days, and his words, that, together with the writing of the voluminous report, took around a year of my life. Some of the key members of the court were Roger Parker, Joe Pope. He was actually Dr. Davidson, I think, when he was called upon. He'd been past president of the ICME. He was one of the 3 youngest presidents in the ICME. He got his FRS in '74, and he worked with Bill Simpson, who'd been chair of the Labour Party, who had suffered himself an industrial accident and was concerned about safety. The other person I want to mention in this was Tom, later Lord Bingham. He was the barrister acting for the court, and what would happen is that Parker, my father, and when they were around, Joe Pope and Bill Simpson, used to meet after the court had finished every day and talk about the plan for the next day, as well as thinking about the overall direction of the activity. Bingham could be pretty tough, when he put questions to the witnesses, they were very pertinent. And there was a memorable point when he said to an eminent metallurgist, a professor not at Cambridge, "You call yourself an engineer." And the poor man didn't survive that long. There were some rigs commissioned, and they were to test this amongst other hypotheses. And as many of you know, Nitro, who were running the plant, were making an intermediate for nylon manufacture. And there were a series of 6 reactors, one of which sprang a leak. And this reactor was removed overnight, again on a Friday evening, and recommissioned. The plant was recommissioned by the insertion of this dogleg pipe. And the flow of fluid from one reactor to the other was regulated by some weirs. So reactor 6 had to be lower than reactor 5, had to be lower than reactor 4. And that was the reason for the dogleg pipe. Furthermore, the reactors were operating at 120 degrees C, so you had pipe expansion, so you had to have some bellows. So the engineers who put this together put some 2 big bellows. The 2 big bellows were normally there to cope with expansion between the reactors, and what they had to do was just to put a dogleg pipe in between. That dogleg pipe was found after the explosion, concertinaed, and a little way away from where it had originally been. I don't think the diagram in the centre is my father's work that shows how the dogleg pipe was supported by scaffolding. But I can remember him drawing the diagram on the right, which appeared in the report, showing the bending moment diagram and the thrust from either end caused by the pressure internally. And the court had to address the question, but was that dogleg the cause of the failure or was something else? And why, if it was, did it actually last for quite a few months before it failed? And the answer transpired to be that the hydraulic thrust from either end, because of the pressure, which was equivalent to about 40 tons, was causing a bending moment, a turning moment on this, which had to be resisted by the bellows or by the scaffolding poles. And I've drawn the scaffolding poles in big blue. And what was happening, they believed, was as the pipe twisted when the thing was pressurized, one scaffolding pole gave way a bit, and then when pressure was reduced, the other scaffolding pole, and it gradually ratcheted until it decided that it had too much. That's the rig that was built to test by Creamer and Warner. And I want to draw attention to David Newland, who was then a professor of mechanical engineering at Sheffield, who became a professor here, who, like Daddy, came top of the engineering tripos here. He did the mechanics of the flight of this thing and showed that that result was consistent with it being taken off before the explosion, so not being blown off after the explosion. There was another hypothesis, the 8-inch hypothesis, and I put this up to show that he could be quite forensic. That 8-inch hypothesis depended on numerous steps, and they all had to work, and some were pretty unlikely. And I remember him writing the famous paragraph 191, which I'd invite you to read. I wouldn't like to be on the receiving end of such a comment. It meant that one set of insurers who insured the original plant did not have to pay up for the considerable damages as a result. Another set of insurers had to pay up because it was a modification. Okay, what was the effect of all of that? All the major operators and the Health and Safety Executive and Commission at that time accepted and acted on the report. And I would suggest that process safety in the UK has been very good by comparison with the rest of the world. This is a graph showing the fatal accident frequency rate on the y-axis against time. This was work in 2017. This is the UK performance. This is the EU performance. And the aircraft industry is often held up as a paragon of virtue in safety. I've had to go at plotting what the aircraft industry result is for the 5 years before this report was done. And you can see that in the yellow triangle. Okay, so let's move on to bubbles. Now, others are going to talk about bubbles. So I'm going to talk more about what work he actually did that had an industrial impact. Before I do, a very brief mention of fluidization from a personal perspective. I can recall, I think when I was about 6, coming down and seeing Daddy looking rather pleased with himself, because this diagram, which the fluidized particle water equivalent of it, had just been drawn out on the drawing board, which showed from quite simple potential flow theory, which John is going to educate you on, is why you get the cloud around the bubble when the bubble rise velocity is greater than the incipient fluidized velocity. That, I would believe, has contributed substantially to the design of fluidized beds around the world. And just in context, quite a lot of the chemical industry does use fluidized bed. The chemical industry does support about 7% of the world GDP and directly about 120 million jobs. Bubbles also had an impact on safety. He did a lot of work on the Rye, and I'll show you some experiments later on. One of his very earliest students doing a Part 2 project with Robin Paul, as David mentioned, he used to use the Part 2 projects as a vehicle for testing new ideas, then went on to work in ICI and eventually ended up, poor man, working for me, on relief valve codes for two-phase flow. That turned into a family affair because Isabel was acting for the Treasury Solicitor, and ICI was keen to pass on the codes to the industry to improve process safety in the industry, and we had to sort out some of the legal affairs. The first bit of plant kit that I put in at Billingham was a Venturi choke that relied on understanding that the speed of sound in a system with a two-phase flow mix was much lower, and how much lower was important. That kit went in and helped to stop arsenic sprays in Billingham for about 15 years without problem. But bubbles really had a big part to play in my life and his in some of the airlift fermenter work, and then later on when I brought him into Tarkside to deal with the titanium dioxide industry. Deep shaft, a brief aside. Conventional sewage works have a digester where you're interested in contacting the liquid with bugs and sewage with oxygen, and the back half of this photo is taken up with classic digester space. And ICI conceived the idea of doing that mass transfer in a vertical tube with the fluid circulating round and round, driven by density difference. And that diagram shows the process air being injected here. And once you've established the flow, and you need to start the flow off by injecting air there, so you establish a flow round and round this loop with the density difference between these two legs. When you've done that, you switch on the process air, and the liquid continues to flow. But there were some instabilities and reverse flow problems which he helped Billingham to sort out. Those things are around the world. I think about 200 were in existence when the patents expired. It's quite difficult to find because people call them by different names. I suspect there are somewhere between 500 and 600 around the world. They're very useful whenever you've got a limited space, which is the truth in both the Japan and the US in this case. A bigger fermenter So Billingham moved on from that deep shaft concept to thinking about how to add value to the methanol process, in which we've had about, I don't know why that, IT seems to alter the slides a bit, but anyway, apologies for that. Billingham moved on to saying, how could we add value to the methanol and ammonia created? And Peter King, who did for his Part 2 project here some fermentation technology, conceived the idea we could find some bugs that would chew up methanol and nutrients and ammonia and make not human feedstocks but animal feedstocks. And these fermenters were scaled up, and this was the biggest one I think that's ever been made in the world, just around 200 feet high, and you can see the dimensions there. Huge, massive steel vessel, and Daddy helped to sort out what the mass transfer problems were inside here, some of the separation issues, and it went up. And Rob Margits, who some of you know, was appointed as the general manager. Unfortunately, there was a sterility problem. This was essentially warm milk, 1,500 metre cubed of it, and for the first 3 months they couldn't get sterility. Rob bounded into my office once and said, "Hey Peter, I understand you're doing my job, or the job I did when I started. Can you help me sort out the sterility problem?" And after 3 rather intense days, it was sorted out, which was actually a slugging problem, which on the pipes to take fluid out, which I would never have been able to sort out if I hadn't done my Part 2 project with him and David Harrison on slugs. That plant came down. It was economically a disaster because after the Icelandic war, fish meal prices came down. But the legacy wasn't all bad. So Rob managed to persuade Marlowe Foods to do a RHM, to do a joint venture, which led to a company called Marlowe Foods. Some of you have no doubt eaten, or certainly seen, Quorn. That's now a nice little business with a £250 million a year turnover. Some of you will have heard of the Novavax COVID vaccine. Fujifilm brought out some of the fermentation facilities, and they've just invested, I think last year, 400 million. And to quote their website, they'll create the largest multi-mode biopharmaceutical manufacturing site in the UK, and that's due to come online next year, which I think is a legacy that actually trying technology can have a tortuous path to success. Another arbitration he got involved in was Pilkington versus PPG. So Alistair Pilkington had developed the process, and PPG, were a much bigger glass company, were rather miffed because he patented things before they'd have done so. So Pilkington's licensed this worldwide, and after the patents had expired, insisted that the licensees keep the material confidential. PPG thought that they could actually help some Chinese companies develop the process or implement the process. And my father was retained by PPG, first of all, to design a float glass process from scratch using publicly available information. And then they showed him where his design would have got wrong. Another Trinity fellow was retained by the other side, and there were some amusing interchanges with my father listening with rapt attention as the other fellow described the areas that they were going to cross-examine him on. And so prepared, I don't think he did too badly. I moved to Tioxide, which was, ICI bought out the half share from another company. And this was a 22-stage manufacturing process for white pigment. Nanotechnology in some ways, if you put all our particles end to end, you'll go 400 light years a year. But this was a 22-stage process, 2 processes, chloride and sulfate. And as my boss first described to me when I came into the job, you would think that the laws of physics and chemistry change from not only continent to continent, but country to country. because the plant managers don't allow their technical people to talk to one another sufficiently. Well, with Daddy and Sid Andrew, another FRS, Chemical Engineering, we posterized the process, and for each one of those 22 stages of operation, for 2 processes, so it was perhaps about 30, some of my father's analyses still rest on in the codes used by the relevant plants to operate and to optimize the design of new plants. One of the research managers, I think 2 or 3 years after I left, said in that period we did 30 years of R&D work, what would have taken 30 years of R&D work in 5, and probably protected about £1 billion worth of assets. Very briefly, I wanted to just show very much a personal view of some of his wonderful experiments. So this was holding a bubble fixed by downward flow. Flow comes in from a constant head tank through some drinking straws and modifies the velocity profile so the bubble sits in the middle. I vividly remember at a Royal Institution lecture, this kit was put up and 3 eminent FRSs were looking at it with some concern, saying, this is too deep for us. They couldn't see anything going on. Well, somebody had forgotten to put the bubble in, so they couldn't see that. Just to demonstrate that he did do some pretty good work right in his last days, I was interested in geoengineering and designing an aerofoil with a foam rear section. As a result of that, I interested him in the flow of foams, and he did some work with some others, but this is highly viscous flow flowing through an orifice, and he developed this lovely theory that predicted or showed very nicely why you got these half-moon crescents in place. Davidson and Schuler was a notable piece of work with a wonderful analysis of how big bubbles are if you have something bubbling into from a pipe into a viscous fluid. And it built on the work that David described of G.I. Taylor's analysis that the inertia of a bubble equals half the displaced mass. Peter Swinnerton Dyer was called in to do the computing. You never saw my father touch a computer or program himself that produced some lovely graphs showing the elegance of the prediction. So finally, what about him and perspectives of the future of chemical engineering? It's an applied subject. He believed that academic chemical engineers should have, when young, some experience of industry. And I think he was a bit dismayed. He said, there are too many engineering scientists at Cambridge. Not enough people like him had actually been out and about and worked with industry. And I should note that he contributed to the design of kit that not only created value, had elegance, but if not designed correctly, could kill people. I would offer that as a challenge to the movers and shakers, the institution, and some others of you in the university, to how to avoid the imperative of publish and perish and bring that about to a greater extent. He helped me create the ICI Young Academic Fellowship Scheme, which was inspired by Roland Clift pointing out that I was then recruiting about 10% of UK chemical engineers through ICI. And we were concerned that you had to be very, very dedicated to become a young academic because the city was paying such high sums and valuing chemical engineers. So we conceived the scheme where, in today's terms, young academics would get paid another perhaps 10 or 15K a year, provided that they could work with grubby industry. So I asked the heads of department of all the chemical engineering departments to submit no more than one a year. And the committee, which was a bit embarrassing because the Institution of Chemical Engineers nominated my father to be a member. I wasn't chair. Jack Richardson was a valued member, and then we had 3 ICI managers. The committee was wonderful because these people would come and we would interview them, and we were told by the chairman to make a list, and with our cross-off pointers, who should get it and who shouldn't. In 8 years that I ran that scheme, at no time did any of the members disagree with any others, so it was a very quick discussion. They gave some of the best and brightest young academics relevant experience, and at one time I think about a quarter of the heads of department had come from such a scheme. And on teaching, he commented, clever contact with, these are his words, clever contact with clever students is stimulating, and their questions are invaluable. He saw the value of Cambridge lay as much as being the development of young talent as research. And for the future, I offer 3 thoughts. One is, I think it's increasingly likely in this world we'll have more cyber attacks around the piece. And actually, if you think about doing it mechanically, it's often possible to devise a system where even if the control system goes wrong, you can protect the plant with appropriate orifices and relief valves. But to do that, you almost always need to have some two-phase flow design around. He thought that chemical engineers should engage more with climate scientists and engineering research on the solar radiation management side. And he was absolutely convinced that the biotechnology mix in the department was the right way to go. I would conclude with some words from an ICI chemical engineer who knew him for 30 years. Your father had an uncanny ability both to coach the inexperienced and sometimes at the same time speak truth to power. He moved easily among all levels in the company and was highly respected for his perspective. He applied himself to problems tenaciously and numerately, often generating new insight with a rational approach. He recorded his interactions meticulously, pricking conscience consciousness on occasion. Those consulting him could look forward to a very gentle but thorough testing of his ideas. And I believe, as the son of a friend here said to me last night, he was felt to be a benign presence. Another acquaintance said he taught his students how to think.
So I think we have time for one question before coffee break, if anybody has one. I'm sure Peter's happy to answer questions during coffee too. So then we'll finish this session. I want to thank all of the speakers again for a wonderful overview, especially people like me who didn't know John Davidson very well. I'd like to remind you that there are tributes that other people have made which are going on the screens, and you can see those both in the CB lounge and also in the atrium. So we're going out here for coffee, and we'll be back here in half an hour, please, for the next session. So thank you again.
I graduated at the University of Birmingham in 1970. My tutor there, the kindly Ken Gray, saw an advertisement offering a graduate scholarship at Downing College. You should apply, he said, so I did. After a visit, Dr. David Harrison agreed to supervise my research and provide a studentship. So in September 1970, I started at Cambridge. I shared an office with Peter Watson, also a Harrison student, working on gas distributors, and Jeff Thwaites, researching turbulent flow with Dr. Nederman. Our office looked out over Pembroke Street and Tennis Court Road. Close neighbours were Ron Mitchell, who designed and made electronic equipment, and the department's photographer, Dennis Pike. Both Ron and Dennis were a huge help in my research. At that time, there were about 30 graduate students in the department. Most were doing experimental work of some kind, gas absorption with Peter Danckwerts, chemical reactors with Dr. Kenny, absorption with Dr. Turner, combustion with Dr. Hayhurst, and various fluid particle projects with Davidson, Harrison, and Nederman. But there was also numerical work. Peter Hutchison and his group were developing the first flow sheeting computer programs, and Dr. Pearson's students were computing non-Newtonian flows. The department had its own IBM 1620 computer, a tremendous novelty, but even this was disdained by the real enthusiasts, who could be seen day and night teletyping with the much larger IBM mainframe run by the University Computer Service. Advised by Dr. Harrison, always greatly supportive, I chose to work on three-phase fluidization. Another Harrison student, Roger Page, was just finishing his thesis on the topic, and there were still many open questions. In 1970, you could read all the three-phase fluidization literature easily in one afternoon, about half a dozen papers, mostly presenting experimental hold-up data. I should explain that a three-phase fluidized bed is a liquid fluidized bed into which you inject gas. Liquid flows upwards and bubbles rise and pop out through the bed surface into a particle-free zone. You can see this on the diagram on the left-hand side, and also the right, which shows a photo taken by Dennis Pike. A basic property of interest is the holdup, the volumes occupied by each of the three phases, gas, liquid, and solid. In 1970, there was no agreed method of calculating these. You had to measure them. However, a useful explanation of the mechanisms at work had been given in a 1964 paper by Dr. Davidson and his student, P.S.B. Stewart. This discussed the mysterious phenomenon of bed contraction. You might expect that injecting gas into a liquid fluidized bed would cause the bed to expand because of the added gas volume. Indeed, this is often the case, but sometimes the bed surface falls. Now, why should that be? Stewart and Davidson explained that gas bubbles carry with them an amount of clear liquid in the bubble wakes. The fast-moving wakes take liquid away from the fluidized particles, and depending on the conditions, the bed can contract. Stewart's thesis presented equations to model this. It was clear that my research needed a new experimental rig to be built. This was a slow business then, a problem only sorted out when JFD eventually became department head after my time. Whilst waiting for materials and construction, I thought about the theory and discovered that variations in liquid holdup propagate through the bed at a finite speed. I was pleased with this result until Dr. Nederman, to whom I was sent for advice, pointed out that Graham Wallis had fully explored the phenomenon of continuity waves in particulate media. Nederman kindly lent me his copy of Wallis's book, One-Dimensional Two-Phase Flow, where it's all explained, a revelation to me. In the summer of 1971, my turn came to give an end of first year 15-minute talk to the department. These talks enabled new research students to get feedback on their project, but were a challenge for inexperienced speakers. I had no experiments to report, only some plans, and a theory which lent heavily on the ideas of Stewart and Davidson and Wallis. After 2 or 3 minutes of speaking, a member of the audience became restless. I was explaining the need to measure bubble velocities to show whether bubbles could be considered as rising relative to the particles, which are on average stationary in space, or relative to the liquid, which itself moves upwards. Dr. Pearson it was who was dissatisfied with this formulation, and he interrupted with the question, "Surely this system is invariant under Galilean transformation?" As I wondered what on earth Galileo had to do with it, Dr. Davidson came to the rescue. He gently explained the Galilean transformation and clarified what I'd been trying to say. The discussion continued with Dr. Harrison and others joining in. Agreement, perhaps a truce, more truly spoken, was reached, and I then finished speaking as quickly as I could. I must say that in future contacts, Dr. Pearson was always very kind to me, and the notoriety of having provoked a debate about transformation of frames of reference soon wore off. But I count this as my first meaningful interaction with JFD, who was to become my internal examiner and postdoc supervisor. Then and in later years, we had many discussions. You always benefited from talking with JFD. His ability to identify the essential features of a problem was quite extraordinary. With a penetrating insight, he shelved side issues and answered the simple question, what is actually going on here? Equations captured the basics, and the simplifications and second-order effects were considered later. The 1964 work on three-phase fluidized bed contraction is an example of this. What is going on is the fast rise of gas bubbles with kilo liquid wakes. The analysis explains not only bed contraction, but the hold-up behavior of all three-phase fluidized beds. JFD's record of published work, more than 200 papers, stretches over an astonishing period of 70 years, from 1949 to 2019. His first paper was written with Alfred Binney at the engineering department. It analyzes the annular jet formed when gas and liquid drain under gravity through a circular orifice. JFD recorded that using Southwell's relaxation methods to solve the swirling potential flow with two free surfaces was a task he found far from relaxing. He also recorded that when he left to join Fox in chemical engineering in 1952, Binney wrote to him, "You have been beguiled by the excellent professor's silvery tones into taking the first job offered to you." But Binney's own career had not been easy. A fine fluid dynamicist, he was demonstrator in Oxford's engineering science department for nearly 20 years. When Southwell left Oxford to become rector at Imperial in 1942, Binney became acting head of department. In 1944, an outsider, Alexander Thom, was elected to the Oxford chair, and Binney moved to a fellowship at Trinity in Cambridge. As soon as he was established in Fox's department, JFD began that series of publications that demonstrated the Davidson touch. It started modestly with a 1955 paper verifying G.I. Taylor's formula for longitudinal dispersion in pipe flow, a student summer vacation project and very neat. But then followed, through the 1960s and 70s, major contributions on gas absorption, bubbles and jets, and much else, including the well-known work on fluidization with David Harrison and their students. A key example is the treatment of particle and fluid flow around a bubble in a fluidized bed. What is going on in this case is that everywhere in the bed, including near to the bubble, the particles remain just fluidized, at incipient fluidization as it is called. A steady flow of fluid through the porous surface of the bubble fluidizes the particles there and moves them aside as the bubble rises. Potential flow solutions for particle flow around a sphere, the bubbles are assumed to be spherical, provide the streamlines of fluid and solids. They predict the bubble rise velocity, the eigenvalue required by the pressure gradient ahead of the bubble. There is a closed circulation of fluid through and around the bubble. Simple, but fluidized beds had been around for at least 40 years when JFD produced this insight that explains so much. Galileo is now considered to be the father of modern physics. His scientific method was based on careful observation and logical inference, striving to substitute a fact-based worldview for mythology, belief, and tradition. This revolution in thought might also be termed the Galilean transformation, one that led to modern science and engineering. The chemical engineering profession was originally devoted to the efficient production of chemicals on a large scale, but now chemical engineers are at work in an ever-expanding arena, addressing challenges like sustainability, net zero and carbon management, energy security, the food, energy, water nexus, global supply chains, fossil fuel chemicals. But we still see the benefit of asking what is actually going on here, clarifying the problem and basing analysis on the answer. Chemical engineering science, of which JFD was such a great exponent, offers many clues to tackling problems, but we need to understand how to apply it creatively to the big new issues.
Our next speaker is Professor Keshavan Niranjan. I'm afraid we as students always said Niranjan, so I hope you won't think I'm being rude. I think we overlapped possibly in the early days. Niranjan worked on bubbles and bubble rise velocity and so on, and he's going to talk about that. And then subsequently, when I had a period in industry, Peter mentioned the corn fermentation. So I was there when it was transferred to ICI to an airlift. And I think we had some discussions on the bubble rise velocity and what was a very troublesome, in terms of viscosity, a very troublesome fluid. So I did get to know Niranjan from his days when he, I think, was at Cambridge, but then moved to the University of Reading. So welcome.
Thank you very much.
Is that okay? So, yes, left and right. Okay, that's fine. Okay. Okay. Right. Thank you very much. Thanks, John. I'll talk about JFD's inspiration and how he certainly inspired me to look into bubbles in food systems. Yes, just my association with the department in Cambridge. Yes, I worked in the department at Pembroke Street between October 1984 and September 1989. And I was associated with JFD from 85 to 89. You may wonder what happened, what I did between 84 and 85. I had a brief stint with Nigel Slater before he decided to immigrate to Holland and work for Unilever. So I worked on an AFRC funded project. Now clearly AFRC stood for the younger members of this audience. It's the Agriculture and Food Research Council. It was the predecessor to BBSRC. So I worked on this AFRC funded project, which aimed to deodorize piggery farm effluent by bubbling air through the effluent. So that was how I got involved in bubbles. And at one stage, my claim to fame was that I was amongst the handful of people who knew how fast bubbles rose through pig and cattle effluent. But I mean, these are some personal observations, and others are welcome to disagree. But I somehow felt that bubbles seemed alive to John Davidson. He almost humanized bubble behavior. And just to illustrate this, incidentally, this is not the thumbnail sketch of the airlift, the recirculating column we had in Pembroke Street, which actually started at the basement of Unit Ops 1 and then rose all the way through the ceiling and ended at somewhere near the office where the secretaries used to sit. But I think I can use this to illustrate what was happening in that column. So it is not an exact replica. So there were obviously it's a recirculating column. So what would happen is you would sparge the gas in the middle, and then clearly you could set up an anti-clockwise circulation, You could also set up a clockwise circulation, and there was a kind of a fairly stable oscillating situation as well, where the dispersion oscillated. But ever so often, what would happen was, in the downcomer, you would have a few bubbles sort of coalescing and forming a fairly large bubble, and that bubble wouldn't rise up straight. It would sort of spiral and really fast. And I was extremely surprised when John called it an unhappy bubble. I mean, I can use many terms to describe a bubble, but an unhappy bubble is not something that would come naturally to scientists, I think. He also called it a diluted bubble. And the reason why he called it a diluted bubble was that it was rising along the wall. So he said it's probably thinking it's in a column which is much bigger than it really is. So it had illusions of grandeur there. And we all know that the bubble rise velocity is proportional to square root of GdE, or which is the equivalent bubble diameter. In this case, in the case of a diluted bubble, all he said was, why? Just replace the diameter by 2d. And what was the observation? The bubble rise velocity of the diluted bubble was 1.4 times the rise velocity of a normal bubble of equivalent size. So the whole theory came from by assuming that the bubble was diluted, and it thought that it was in a bigger column than it really was. So it was a very simple explanation and clearly illustrated the way John Davidson thought. He was also, the way he structured the flow of gas through multi-phase systems was also quite unique. In the case of fluidized beds, we all know that, the basic assumption is that, the gas sort of, a part of the gas, so the gas divides itself into two phases. A part of the gas essentially goes to fluidize the solids, and the remaining part probably goes through as bubbles through the fluid that has just been created. That in a nutshell is the structure of fluidization. So most chemical engineering models, they treat the gas, liquid, and solid as sort of separate individual phases. We may talk about partial pressure gradients, we may talk about temperature gradients, etc. But John could really visualize the gas itself dividing into subphases with different functionality. Now that is quite unique. And if you accept that as a hypothesis, then the similarity of bubble rise in solid and liquid, which was a very fundamental work which John authored, almost follows as a logical corollary of the hypothesis. Now, in the 1980s, yes, John got quite interested in viscous liquids, and in these viscous bubble columns, I'm quite pleased to see Zhao Min and even Franz Müller over here. So they did the work on these viscous systems. You have extremely large bubbles, but you also have very large wakes behind these bubbles. And John said that the liquid behind the bubbles gets a free ride with the bubble. Again, it's a very sort of an intimate description of what was happening in the column. But that wasn't what's happened here. So the conventional view as far as mass transfer in these columns was that, so you had these large bubbles, but when you bubbled the column for a while, the whole liquid became turbid after a while. So the general view was that these tiny bubbles, they remained there for a very long time, so they more or less attained equilibrium with the liquid, so they hardly contributed to mass transfer. So that was the general view prevailing at that time. But John Davidson took a very, very different view, and he said, no, a finite fraction of the gas sparged flows in the form of tiny bubbles, which can coalesce and disengage from the liquid. So there is a dynamic equilibrium that exists between, those bubbles, those tiny bubbles, were not the same bubbles. There was a dynamic equilibrium, and therefore there was a time constant, and whether the tiny bubbles were in equilibrium or not depended on whether the time constant was high or low. So this was John's idea, which was very, very different to the conventional view. I just expanded that view and came up with a dimensionless number, and which compared, the mass transfer coefficients, which compared the residence time of the bubbles with the time taken for mass transfer. And this, if the dimensionless number value is high, then clearly the bubbles were in equilibrium. But if it was low, the bubbles were very active, and they were not just very active, they were immensely active because the interfacial area was extremely high. And experimentally, in impeller agitated vessels, I showed that more than half the mass transfer occurred through the tiny bubbles, whereas the reactors are actually designed on the basis of the larger bubbles. As a chemical engineer, as an old-fashioned chemical engineer, I get very excited seeing dimensionless numbers, and I thought we chemical engineers do generally honor our grades by naming a dimensionless number after them. I don't know whether there is a Davidson number, and I'm sure there are many, many candidates for a Davidson number, but this can probably be one. So this idea that the gas divides itself into different subphases is something that I took with me, and when I joined the food science department, I was looking for problems where, in food sciences, they had, even though they were using bubbles or gases, they really hadn't recognized the fact that, gas is a food ingredient. And the gas was actually playing a very critical role in defining the structure, the stability, and the mouthfeel of the product. So the first problem that I got involved was with Rankovic McDougall, and they were, this was in the baking area, so they were making a sponge cake, and clearly the sponge cake batter was being aerated, and they were having some problems. So I was just looking into that problem, and in that context, I looked at the dynamics at which the gas holder builds inside a pressure whisk. Incidentally, this is not the holdup when the whisk is working. What happens is you aerate the batter, it's the whisk that aerates the batter. However, the whisk is then stopped, and it's the bubbles that are entrapped which really matter as far as baking process is concerned. So we developed a model for the entrapped bubble. How that varies as a function of time. It was just a simple sort of Davidson style differential equation where the rate of change in the holdup of the entrapped bubble phase was given by this equation. I don't want to go through all the details here, but if you solve that equation, you get the gas holdup going through a peak and then coming down. So clearly the time for which you aerate the batter depends on how much gas holdup you want. And it's not just that, because we are going to be baking after aeration. So the extent of aeration was quite critical, and that's where the company was getting different sometimes the cake would puff, sometimes it would puff and then collapse completely. So determining the time was actually quite critical to the process. We chemical engineers get very excited when we see turning points, but I can tell you that if you stop aerating when the holdup is at its peak, you can see a puffed up cake in the oven, but as soon as the process is over, it becomes completely flat. So that's not the point where you aerate. So it's here that chemical engineers have to talk to food scientists, especially those who are working in the sensory area, and that's how we determine what should be the optimum time for mixing. Nobody eats a cake because a clever chemical engineer has aerated the batter. We eat a cake because we like the cake. Now, Davidson's models for bubbles in liquids are essentially hydrodynamic in nature. In other words, it's the dispersion is created by hydrodynamics, and to some extent, and it's not very sensitive to the chemical nature of the gas. So if you are talking about using air or using carbon dioxide or any other gas, the structure is more or less same in a bubble column or in an impeller agitated gas liquid reactor. In the 1980s, the food industry moved from batch aeration to continuous aeration, so you have a mixing head here, and in the mixing head you have the liquid phase or the continuous phase, and then gas being injected, and then the mixing head works under a fairly high pressure of about somewhere between 7 and 10 atmospheres, and the food industry was also using a range of gases: carbon dioxide, nitrogen, helium, nitrous oxide. So these are all different gases that are being used even now. So the dispersion characteristics were not actually determined by the hydrodynamics, but it was actually determined by mass transfer, because what was happening was that under pressure, the gas was dissolving in the continuous phase, and when you release the pressure, the bubbles were released, and that's what caused or created the structure. And the bubble sizes were orders of magnitude smaller than the Davidson bubbles. Some people call it micro bubbles, but that's just a terminology. So what this meant was that under the same hydrodynamic conditions, different gases would give very different dispersions in a given continuous phase. So what you can do in theory is to simply, you take a base recipe and you can aerate it with normal air or carbon dioxide or helium or nitrogen. So simply by changing the gas, you can change the entire structure of the dispersion. So we had a project that was funded by Nestle, and here we took chocolate, and incidentally, the base recipe for the chocolate was the same as Yorkie. Remember, bubble-containing Yorkie is actually aero. So so we took the Yorkie base recipe and then created a bubble-containing structure using 4 different gases: carbon dioxide, nitrous oxide, argon, and nitrogen. And you will see that very broadly speaking, the holdup or divides itself into 2 sort of into 2 categories. With carbon dioxide and nitrous oxide, you have fairly large holdup, whereas with nitrogen and argon, you have relatively small holdup. Again, the bubble sizes with carbon dioxide and nitrous oxide were relatively large, whereas with nitrous oxide, you got relatively small bubbles. What this meant was that, the mouthfeel was completely different. So the base recipe was the same, mind you. It's only the gas that was used to create the structure was different. Incidentally, the gas is not trapped. The gas escapes, because the gas creates the structure, and then it escapes, and it's just a porous void, which is filled with air. So you're not biting into the gas as such. There was somebody who asked me whether they could do this with helium and trap the helium, because if you then bite the chocolate, you start speaking like chipmunk. So, but that's something which I have not succeeded, but that's a possibility, definitely. So you have 4. The point was that simply by changing the gas, you can create products which are perceived very differently, because they have very different mouthfeel, very different flavor profiles, and very different even taste. And so the eating experience or the consuming experience is very different simply by changing the gas. Now, the other thing is that the Davidson's dispersion models are also not critically dependent on interfacial phenomena, because he largely worked on large bubbles, whereas we are more interested in looking at small bubbles. So what I did was to look at the structure of milk foams, and you can see and we use confocal laser scanning microscopy to look at the interface, because that becomes very critical. So here you can see, at 4 degrees centigrade, milk foam, and you can see the fat globules. at a higher temperature, the fat stabilization is replaced by protein stabilization. In fact, the protein also, basically gets denatured, and therefore, in the normal Starbucks cappuccino form, it's the protein and the whey protein and the casein, they form a network, and it is that network that stabilizes the form and gives you the rich mouthfeel that we all seem to have got used to. You can also look at microbubbles simply by looking at the debris that is left after the escape of the gas, and this is what is called bubble ghosts. So that's another technique to look at the interface. Finally, the food industry is now very much excited with what we call nanobubbles. If you look at the normal bubbles, you have the sort of a normal internal pressure, and you also have the Laplace pressure. When the bubble size becomes very small, the curvature is very high, and therefore the Laplace bubble pressure dominates. And you will see that if you take a 100 nanometer bubble, the Laplace pressure is almost about 30 atmospheres. So you can get extremely high driving forces by creating such bubbles, and that's something that we are looking at. I've not yet started experiments in this area, but certainly the food industry is very excited about it. And so what are the take-home messages? Well, bubbles in foods are as alive and kicking as the conventional Davidson bubbles. John Davidson always endeavored to simplify complexity. He never complicated simplicity. That's a very important message. And lastly, I find that in the food area, our measurement capability has expanded significantly, but our interpretational capability is very limited. In fact, I would go to the extent of saying that our measurement capability, the disparity between measurement and interpretational capability is quite grotesque at the moment in the food area. But John Davidson was all about both measurement as well as interpretation, but he always measured things on a scale that mattered. So that's my final message. Thank you very much. Sorry,
Thank you very much, and that's a real tour de force. I've got loads of questions, but I'm afraid we can't answer now. So thank you very much for that. So our next speaker is Professor Dame Lynn Gladden. Lynn, of course, is not only one of the foremost researchers, I would say, in the world, certainly in MRI, but has sometimes been head of this department, PVC for research at this university, and now heads the EPSRC. And yet, through all of that, she has maintained her research output back together with the significant MRI team. So, really, over to Lynn.
Right. Thank you very much for that kind introduction, John. And it is indeed a privilege to be asked to speak to this group today, and to be able to in person say a huge thank you to John for everything he did for this department and everything he did for me personally. And so I've called this Fluidization and Bubbles with JFD. I was originally given the title Magnetic Resonance Imaging, but I very much want to focus it on what we did inspired by John and in collaboration with him. And I certainly, as you will have gathered from that interaction, do not do this work alone. And I work with Mick Mantle and Andy Seederman very much as a team, and also want to thank the many, many PhD students and postdocs in my group and with other groups in ChemEng, both here in Cambridge and around the world. So let's onwards. Oh, and yes, and I should also say that if one is talking about John, for me, it was also about John and Suzanne. And I would often go round to their house, and Suzanne would show me her Harrods shopping bag, which she kept her bread in. And I was always hugely impressed, and it gave me something to aspire to. But they were an absolutely splendid couple who really had priorities right in life. So, JFD and the Magnetic Resonance Research Centre. Probably the most important slide, really. I will always remember my job interview, the formal interview. I'd had a preliminary interview with John on one Saturday morning, which was in itself entertaining. What I learned for the formal lectureship interview was be really careful what you agree to. So he scratched his head at me, as he was wont to do, and said, well, of course, and I echo the words of earlier speakers, you will have to learn chemical engineering. So I like a lamb to the slaughter, saying, yes. So I was coming in from a physics and a chemistry background. And he suggested that the best way of doing this was, if I were to be offered the job, that I would give examples classes in every part 1 lecture course in chemical engineering with immediate effect. And again I go, yes. Now, it had a touch of the nightmare in reality about this, but I would never have actually engaged with chemical engineering as a discipline if I was just told, well, read around the subject, get to know what we do. And it was really important. And twice a week, I had to face undergraduates in the department and pretend I knew what I was talking about on subjects I'd only learnt the night before. So nothing changes as one goes through life. But what it also taught me, and again this echoes things that others have said today, is that, what's distinctive about chemical engineering? There's certainly a distinction in terms of we look at things as overall systems, but it's also about the coupling of chemistry and transport processes. And that's what I think is really special about chemical engineering. And during that period of the first 2 years in the department, what I was able to do was look at what chemical engineers did, and they were very sophisticated at developing models and increasingly simulation codes. But this was at a stage where they hadn't picked up on some of the emerging measurement techniques. And so we moved into an area of magnetic resonance imaging, where obviously in the hospitals it was looking at the internal structure of what was going on in the body and the chemistry occurring, but also the blood flow. And so the challenge was, how do you take that and modify it to look at chemical engineering systems, both in terms of classic chemical engineering areas and emerging ones? And John was absolutely instrumental. He would have known nothing about the technique, but he just said, well, if you think it's the thing to do, go have a go. And was so hugely supportive of what we did. So we started off in a staff office, one machine, in a staff office on the 3rd floor of Pembroke Street. We then got another spectrometer system. And whilst a lab, the Magnetic Resonance Research Centre, which is what we've got a picture of here. Is that the thing? Oh my lordy, what have I done? I won't, you see this? Which is the, there it is. That's I'm not in control of this. There's the green one. Right, so that's the Magnetic Resonance Research Centre. And as many of you will know, there was an uproar, there was a riot in the locality because there was a very smart housing estate that had been built on the back of that site. And the residents who had paid large sums of money for their houses decided that a nuclear research facility was about to be installed. And it was really very, very challenging, actually, to get this through. And John's support, interacting with the council and speaking on behalf of the research that we were doing, and making some very compelling scientific arguments as to how it was safe. So there's one particular calculation which he did, which said, you're not exposed to you're exposed to a magnetic field of the order of that which your head is exposed to when drying your hair with an electric hairdryer if you sit on the roof of the building, right? Now, you would think this would win the day, to which some of the locals said, yes, but we don't dry our hair all day. So anyway, again, John related this back to me and said they really are a very tough bunch, Lynn. So anyway, the Magnetic Resonance Research Centre was built, and then we got more kit in, and I'm just going to show you this video, not because I've suddenly taken up rowing, but because there is a University of Cambridge video welcoming people, encouraging people to come to Cambridge. And if you click on that on the university website, it highlights this department, because it's obviously now a fantastic department we're sitting in. But actually then it sweeps down into what is the NMR lab in this department, which is down in the basement. So you'll have to get used to the sickly music as well. But again, none of this, the point being here, that none of this would have happened without John. And if you do actually notice the magnets in the magnet hall, there's about 4 or 5 of them, And nowadays, inside those magnets, we will have working catalytic reactors and carbon sequestration processes. But as I say, today I'm going to talk about the work we did with John. So let's just... There's ChemEng, Biotech. And there we go into the magnet. None of that would have happened without John. So, let's move on. I want to look at 3 things that we did in collaboration with John. And you can see, if I manage to mess this up again, there's the pointer, some really dodgy customers up there. And there are quite a few of them in this room. So there's the good John Dennis over on the right as you look at it. There's Alan. And then we've got the good Professor Fennell from Imperial, who's just got a long service award. He just told me about this, and I thought, God, I'm really getting old. If young Fennell has got a long service award. So this is about 15 years ago. Stuart Scott, Christoph Muller, all these guys who have gone off to have very successful academic careers. And so this was a collaboration between our team in the magnetic resonance group and the fluidization group. And of course, John was part of that. So if I just play that again, let's get it behaving. He didn't want to play, does it? Anyway, it did play once when I clicked it. So let's just flip back. It's a very old video, and it's having... There it goes. So what you're seeing there is signal from the seeds in a fluidized bed. So these were the sorts of fluidized bed systems you would have had in unit ops, but we're now taking that system and putting it inside the imaging system of an MRI system. And it's the oil within the seeds that you're getting the signal from. And so you're seeing the bubbles and the slugs within that system. And you can look at different parts of the bed. So the nice thing about this is it's an imaging technique where you can look at the full 3D system. I'm just showing you a 2D video. We would now get that in 3D. And also you can now measure, encode every particle with the actual velocity with which it's moving at every point in that video in the X, Y, and Z directions. And so not only do you get a lot of insights to actually challenge existing theories, but you also get fantastic data sets against which you can compare the predictions of numerical simulations and indeed get insight as to how you implement those simulations. And that really, in a nutshell, is really the way we go about the work in the magnetic resonance group. But a lot of it started around this area of granular systems. So if I just take a step further forward from that, that's just a breakdown of four of the images that were required. And I always like this one because the whole thing's slowed down sufficiently that you can actually see the bubble and the slug, the bubble meeting the slug and opening up, and then joining, forming the bigger slug. So that's just to give you a feel for the type of data that one can get back. Now, I am not an expert at fluidization, so many of those in the audience will cringe at the clumsiness with which I use terms describing fluidization. But what we have here was something which was about understanding bubble coalescence and slug formation. So this was, again, work done with the fluidization group. And just to understand these diagrams, what we're doing is we're just looking at a vertical profile of the solids in the bed. That's what's giving a red signal, a high intensity signal. And so if we are passing gas through below the minimum fluidization velocity, there will be no fluidization, and you will get a flat surface defining where the seeds are and the gas above it. And so what you've got are many hundreds of vertical profiles of seed and gas distribution here as you go along one of those. Okay, so let's now increase the gas velocity to slightly above that of minimum fluidization. And what you'll see is what we've seen in some of the pictures earlier from other speakers. You start seeing essentially particles breaking through the surface. The surface looks as if it's beginning to start bubbling. pass through more gas and things get really quite overexcited. You've got lots of stripes there, lots of particles breaking away through the surface at the top. And so what is that telling us? Well, that's a very expanded region from that, one of those high velocity regimes. And let's come across here to a schematic of the fluidized bed. And what we see here is that the top surface of the bed, that would be high signal intensity red interfacing to the gas phase above it, which is blue. Okay, so that, as we track it in time, is therefore the rise velocity of the dense phase. If you look at what's happening there at this interface, the slug-solid interface, you've got the red, which is associated with the particulate phase, and then the less dense phase, which is the slug phase. And so that's the interface between red and blue. So in terms of those 2- and 3-dimensional pictures of the bubbles and the slugs and their velocity, you can also do different types of experiments where you are just tracking the evolution with time and therefore the rise velocity in situ of these bubbles and slugs and also of the dense phase. Now, why were we doing this? Well, frankly, it was reckless to do it. We were going to check that JFD had got the theory right. So you can tell that he had. I wouldn't dare show it at this symposium if he hadn't, but who would doubt that he could possibly have got it wrong? And the controversy was all about when you should include the additional term U minus UMF. So the additional gas velocity above that for minimum fluidization. And so if we go to this slide, I'll also show another much more complicated picture here where, and I'll just talk you through it, there's a lot going on there. It's a lot more complicated on the previous slide. And what you're seeing there is that you can track in real time the coalescence of the bubbles. You can monitor their dimension, because that will be given by the vertical distance at any point in time. And this line here is the rate of advance as the bubble, or the increasingly large bubble, moves up the column. And so what you'll see here is that you get a deceleration upon coalescence, and then post-coalescence, you'll get a speeding up of the bubble again. But again, you're seeing this from the heart of the column. You're not just having to look at what's going on at the walls. And there is the rather congested slide. But what we see, and of course, you know, we've mentioned the David Harrison book and much other work by JFD in this space as well. But the controversy here was, did you actually need U minus UMF to describe the rise velocity of the isolated slugs? And of course, he had already explained and predicted this line here, which was for the single bubble rise velocity. And actually, the experimental data of the circles, and what you're seeing here is just above the distributor, you get a lot of coalescence events, so things look as if they're jumping around, with those acceleration, deacceleration, and acceleration phases. Then, further away from the distributor, life calms down a bit, and the bubbles just rise, and then you move into that slug formation region. So the answer was, John was right. And we all breathed a hearty sigh of relief and moved on. And then this one I thought I'd finish up with, and some of you will have heard me tell this story before. The glass is there for a reason. I was having lunch with John and some industrial visitors in the university centre, so many moons ago. And we had our pre-dinner drinks, which were, of course, not gin. They would have been sparkling water. And there was probably a slice of lime in it. And we were busy chatting. And then suddenly, John went completely silent. And he was just staring at the glass. You guys know why he would be staring at the glass. The other people at lunch hadn't got a clue. And he just stopped talking and he stared. But this went on and on and on. In the end, they were saying to me, "Is he all right?" And I go, "Yes, he's fine." And he carried on a bit. And then I said, He's looking at the bubbles. And that sort of woke him up. And he goes, yes, it's fascinating. And it really was, because I'd looked in his glass as well. And these bubbles were dancing all over the place. It was just like a particular configuration, probably, of a lump of ice and a piece of lime. And it was, the bubble dynamics were absolutely stunning. And he was just lost. And I'm thinking, he's just sitting there doing the maths. I know it. And so it turned out that a few years after that, we found out that there was actually still an unsolved problem in fluid mechanics, or there was an area of controversy as to why bubbles wobble when they go up a pipe, okay, or in your glass. And I think I'm going back to what Peter was talking about, because we had to design that experiment to study this, because we didn't have a fast enough technique to be able to study the flow fields around these bubbles in real time. If the bubble was rising, it would go out of our field of view very quickly. And so that diagram that Peter showed of creating a downflow into the column held the bubble stable while still letting it oscillate. Okay? And so you're just meant to admire the pretty picture here. I'm not about to give you a fluid mechanics seminar, even if I was competent enough. Right. So, this is where we were getting the MRI too. And I see Andy Seidman. I don't know whether Mick's here as well, but Andy would have been highly instrumental in doing all this. And so what you can see is the colour map is showing you the Z component of the velocity. And the little arrows are showing you the XY vectors of the velocity. And you really do get some truly beautiful pictures here. I've just blown that one up. Even I think that's beautiful. That you can actually capture that information. You're not putting any dopant into that system. You're just imaging it as it is. And you're capturing it effectively in real time. And so you can see these counter-rotating vortices in the longitudinal direction, as well as the vortex structure, secondary vortex structure in the horizontal direction. Okay, so there is our video again. And what you can then do is you find that actually, if you plot, as we have done over here, essentially the bubble orientation, and also then the direction, the behaviour of the secondary vortex, you see that the two are inversely coupled. And so the secondary vortex in that horizontal direction is reversing direction following every wake shedding effect, and that's what then flips the bubble. And we resolved said long-standing controversy in the world of bubbles wobbling. But I think, again, it was just that simple way of holding a bubble stable, which was actually key to being able to do this experiment. So, hopefully I've given you a flavour for the things that we did with John. Again, a massive thank you to him. He's been an inspiration and will continue to be an inspiration to all of us who have worked with him. Thank you.
Thank you very much, Lynn. I don't know whether we ought to just take, if anybody's got any pressing, just one question, if anybody wants to ask Lynn a question. Okay, thank you very much, Lynn. I've got a number of questions to ask, but I'll leave those till lunchtime. Our final presentation is from Roland Clift. Roland has a place in my heart because he lectured me when I was an undergraduate, particularly on fluidization, and actually he talked about unhappy slugs as well. So he obviously had a bit of a personal feeling for fluidized beds. But Roland then left the department and became head of department at Surrey, and amongst other things at Surrey, he sort of was one of the pioneers of sustainability, and in particular sort of logical thinking about life cycle analysis. He is now in, I think, British Columbia, isn't he? So he's in Canada, but I'm sure he's lost none of his Raider-like insight into technical problems. So take it away, Robin.
Good morning. I'm very grateful to the people in the department at Cambridge for giving me a chance to contribute my appreciation of John Davidson and something about his significance to me personally. To tell you who I am, I was a student at Cambridge from 1960 to 1964. I read Natural Sciences Part 1 and Chemical Engineering Part 2. I was back at Cambridge as a lecturer and a fellow at Trinity from 1976 to 1981. I then moved to the University of Surrey as head of their chemical engineering department and subsequently set up what is now called the Centre for Environment and Sustainability. I retired to the west coast of Canada about 4 or 5 years ago, and I am recording this in Victoria, in British Columbia. And that's why I am not with you in person, but I'm delighted to contribute. So, to my relationship with JFD, and I still think of him as JFD. We first met in 1961. I had gone to Cambridge to read physics, but I'd rather lost interest in physics, and I wasn't sure what to do. One of my fellow students at Trinity, David Lickley, knew about chemical engineering, and he suggested that it might be suitable for me. So my tutor sent me to see the Director of Studies, who of course was one Dr. Davidson. Dr. Davidson told me about chemical engineering, and I thought it sounded the kind of thing I was looking for. So it was John who actually got me into chemical engineering. That is already a lot to be very grateful for. But of course, it goes a lot deeper than that. John was one of my mentors all the way through my career. He was always very supportive of me, even when I went off into the wonderland of transdisciplinary research. And even though he was a bit skeptical of the value of doing that, but he was always supportive. I only published one paper with him. It's on the gas flow through bubbles in fluidized beds, and hardly anyone has ever cited it. So his significance to me is at that more generic level. When I was thinking about why he was so special, I thought it would help to line him up alongside some of the other people who have influenced my thinking and professional behavior. So that's what I'm going to do. And the first of them is a medieval philosopher, William of Ockham. Of course, we have absolutely no idea what William of Ockham looked like, except that he was a Franciscan friar. This particular picture of him is from a window in the church at Ockham, which is the village where he was born. Ockham is quite near Guildford, so when I was at the University of Surrey, I thought of William as a local lad. William was a proponent of the doctrine of nominalism, which is the principle that objects exist, but there are no universals or general ideas. He maintained that universals are only labels. This is actually a very unsettling and unpopular principle, and in fact it was seen as heresy at the time. But nevertheless, he was fearless in promulgating his views. That's why William of Ockham is one of my superheroes. I also think there are interesting links between nominalism and 20th century existentialism, but don't worry, I'm not going to go into that one right now. Ockham is best known these days for a principle that has become known as Occam's razor. It only acquired that label 300 years after his death, so there's no definitive statement of what exactly Occam's razor is. The general idea is that when there are competing explanations of some phenomenon, the simplest explanation is to be preferred. The version I've given you here is the one that I think is most applicable to research in science and engineering. And I see it as embodying John Davidson's approach. So let me enlarge on that. My next personal mentor was Leopoldo Massimilla. Leopoldo also worked on fluidization, so you may have heard of him, and if you've been around a long time, you may even have met him. He sadly died nearly 30 years ago. He was head of one of the two departments of chemical engineering at the University of Naples, and I spent a sabbatical year there in 1973 to 1974. Leopoldo was remarkable because he was a huge influence in the University of Naples, but he was completely honest and incorruptible. And believe me, that was quite difficult in Italian universities in the 1970s and 80s. He had a great sense of humour, and you can probably see that from the photograph, and he had a very sharp eye for anything pompous or ridiculous. He was a true Neapolitan, actually. With hindsight, I realised that his sharpness and also his scientific ability came because he applied Occam's razor to the sort of complicated pseudo problem that arises all the time in university politics. Again, I only wrote one paper ever with Leopoldo, and it has no particular significance. But for me, more than anyone else, he showed me how to use Occam's razor to cut through the web of university politics. And the last person I want to mention is my late friend and colleague, John Grace. John, of course, was another fluidization worker. He did his PhD at Cambridge and graduated in 1968. He then went to McGill University, which is where I met him, and we worked together for some years. He was the dominant figure in Canadian chemical engineering right up to his death. We co-authored a book with our colleague at McGill University, Marty Webber. That was Bubbles, Drops and Particles, published in 1978, and it was a huge success. 10,000 citations in the scientific literature and still counting. And the book set us both up. The particular significance for me was that it established me so that I could go off into a different direction, into the wilder world of interdisciplinarity. I worked with John for years. It was a huge pleasure to work with him, although we had rather different personal and writing styles. For example, he was very reluctant to follow Occam in being overtly polemical, whereas I think it is the role of the engaged intellectual to be polemical, and in that I follow Edward Said as another of my mentors. But, and here's the point for now, John Grace was someone else who was very adept at wielding Occam's razor to the cut to the heart of a scientific problem. So the theme here has been Occam's razor. I've introduced you to the source of the analytical tool and to three colleagues who used it to good effect. The common theme is personal and intellectual integrity and the ability to get to the heart of a problem. So now back to John Davidson specifically. This is my favourite picture of him. I took it inside the shell of a huge fluidized bed reactor at Arad in the Negev desert in the south of Israel. We were there as expert witnesses in a legal dispute. And of course, our analysis of the process centering on this fluidized bed reactor drew on the two-phase theory of fluidization. In the photograph, John is holding up a pickaxe to show the height of the splash zone, which was indicated by the erosion on the refractory lining of the reactor chamber. So this brings me back via John's work on bubbles in fluidized beds to what I think is one of his most significant papers, and that's his model of particle and gas motion around a bubble in a fluidized bed. That paper really exemplifies this version of Occam's razor. Of course, the Davidson model is not perfect, but by cutting out the confusing detail, it provides an understanding of what is going on. And that's really the important thing. And there is actually a very revealing corollary here. In the 1980s, when I was still involved with fluidization, there was a lot of stuff being published on computational fluid dynamic models of fluidized beds. It may well be that this work is still going on, but I wouldn't know because I've been out of that field for 30 years. I personally don't think that the work gave anything as useful as the insights that came from the Davidson model. But it did lead to a very interesting meta-experiment to compare different models. the modelers were invited to simulate flow of gas and particles under particular conditions in a fluidized bed. And once they had sent in their model predictions, the experimental data for the actual gas and particle motion were revealed and compared with the models. And surprise, surprise, the models with the smallest number of fitted parameters gave the best fit. That really, I think, amounted to an empirical validation of Occam's razor. Now, John himself was far too savvy to get involved in this sort of multi-phase modelling. That's perhaps surprising, given his early involvement in modelling flow through turbines, but he had the wit to stay out of it. I think he realised that it was much more informative to focus on understanding the basic phenomena. I suspect this was an approach that he learned from an earlier Cambridge figure, G.I. Taylor, but we don't have time to explore that one here. However, it, I think, exemplifies why using Occam's razor to get unnecessary information out of the way was a very important tool in John's approach to research problems. So I will end by giving you an alternative formulation of Occam's razor, which I think sums it all up. I think of this whenever I read some of the current work on other fields, which I have to read these days. It's terribly clever, but it's unnecessarily complicated, and sometimes it's even pointless because the researcher hasn't thought about what they are doing and why. So I leave you with this articulation of Occam's razor, which I think epitomizes what John Davidson contributed. Please think before you put a lot of effort into being terribly clever. Thank you all, and big thanks to our mentor, John Davidson.
Once again, I hope we can send our appreciation to Roland for that. He's lost none of his edge, I think, over the years. And I remember him actually quoting Occam's razor, or his version of it. Not the thing that people use to be clever bit, but certainly in our lectures he did quote it at one stage, and not to multiply problems beyond their putting too many entities in. So I'd really like to thank all of the speakers we had this morning. It's been a really brilliant insight. I almost feel that John is sort of sitting in the room with us, and I'm sure he will have some comments to make as well, if he were. So once again, thanks to the speakers, and if I can just a round of applause for them.
All right, let's try to start. Maybe I'll come to the microphone so you can hear me better. Hello everyone, I hope you enjoyed the lab tours. My name is Eva Marek, I'm an academic here now. I'm an academic at this department, working closely with John. I will introduce myself later again because I speak at the end of the next session or in the middle of the next session. Now I'm chairing this one, so we're starting the next session by talking about John Davidson's legacy and how it drives the vision of the department in the future. And we have three amazing speakers.
No pressure.
Starting with Professor John Dennis, who doesn't need an introduction, but let me introduce him nevertheless. So John did his MEng and PhD here at this department. He did his PhD with Professor Hayhurst, with Alan, who we had earlier. But John also collaborated very closely with Professor John Davidson. After PhD degree, John immediately started his lectureship at this department. Then after a few years, he left the department to go to the industry. There he survived only 3 years, coming back again to the department, taking again lectureship. 10 years. Your biography is wrong then, John, and it's recorded. Apologies. And then John went through a series of promotions from lecturer to senior lecturer, reader, professor, then head of the department, and now head of the School of Technology. And I have a great pleasure of collaborating with John closely, and I'm 100% sure you're going to enjoy this talk.
Well, thank you very much, Eva. And I have to say, it is a great pleasure to be collaborating with you in research. And in fact, one reaches a stage where one realises that one's junior collaborator has become the senior partner in the organisation, and I'm expecting great things of Eva. Okay, so as Eva said, this afternoon is about where is the department going. So this is starting off the session really on the CV of the future, and how John Davidson's legacy informs that to some extent. So where did I get my research from? Well, what I've tried to do is to formulate some, if you like, guiding principles from JFD's work. I particularly reread his 1995 and 2020 papers. The 1995 paper was, in fact, the Danckwerts lecture that he gave, and the 2020 paper was actually the paper that was published posthumously. But of course, I've had many conversations with John over the years, and certainly over tea, which one of his favoured forums for discussion. I'd then like to ask how those principles might inform the vision for CB, take a very brief look at what I think are some of the major research challenges, and I think they've been touched on already, and also how those challenges might also shape the teaching curriculum. And I will emphasise, since I'm not head of department, I'm head of school, this is a personal view. So really moving first of all to teaching and research, John believed passionately, I think, really, that teaching and research had to be inextricably linked. And I particularly like the first statement here. So these are extracted from his two papers. Academics grumble about what is disparagingly described as the teaching load, but I believe teaching is uniquely helpful to research. And he goes on to say, and I think we've heard this before, that contact with clever students was stimulating. And of course, students ask those embarrassing questions that one's colleagues are too afraid to ask. And that, again, is a further source of stimulation. My own belief is that with the multidisciplinary challenges ahead, and more about that later, I think teaching does need to be informed by our research. And I think our research needs to be informed by fully understanding the fundamentals so as to specify the research problem in great detail. This is, in Rowland's terms, this is making sure that Occam's razor remains fully whetted. I think also that to train the leading thinkers of tomorrow, teaching can't be relegated to teaching only staff. And this is, I'm not saying this is a trend in this department, but it is a worrying trend in the university. I do think that people that teach need to be both research and teaching. And I suppose the classic example from JFD, which has already had an airing, but it is worth just repeating. So in the early days of fluidization with fluidized bed reactors, the question was, how did gas bypass the reactor? So basically, John Davidson and David Harrison considered the case for a single spherical bubble rising in a sea of particles at minimum fluidization. So these are particles that are just separated from each other, so the interparticle forces have gone to zero, and so that was the particulate phase. And the assumptions they made were to really boil this problem down into very simple terms. So, as we've seen, imposing a downward flow on the system has been used experimentally. It was also used theoretically in this. So, a downward flow of particles was imposed so as to analyse a stationary bubble. The second major assumption in this was that it was assumed that there was a constant void fraction in the particulate phase, and often denoted epsilon mf. And that is quite a plank in this theory, and of course from that the two-phase theory of fluidization comes from. But John, of course, also realised that if that were the case, it might well be possible to treat both flows independently as inviscid compressible flows, and therefore potential flow theory, which was a key part of the undergraduate syllabus, could potentially apply to this process. So without going into a great big lecture on this, basically they formulated Darcy's law in its general form. Here V is the gas velocity, U the particle velocity, K is a permeability constant, and PF is the local pressure in the gas. And because of assumption B, you can also write the continuity equations for that system in that form, also assuming that it's time invariant. And what you can do is, from those two, you can derive equation 3, which is basically Laplace's equation. And the beauty of equation 3, which might have been lost on lesser mortal, but wasn't lost on John, was that it basically saying is that the fluid pressure field is completely unaffected by the motion of the particles, which is a really interesting insight. Well, anyway, really using the undergraduate approach, so the particle flow, a standard potential flow result would arise for a sphere in a uniform flow, and that's equation 4. And basically, you can put 2 to 4 in 1, and you can obtain the stream function for the gas stream function for V. And that is of the form I've given here. What this is basically saying, without going into it in great detail, is there is an RC, that's a radius out here somewhere, which is labelled in the original Davidson-Harrison book as the limit of penetration, and you can obtain an expression for RC. What it's saying, though, is that gas leaves so these are the gas stream lines, the dotted ones. The gas leaves the top of the bubble, goes round and comes back into the base of the bubble, and so actually rises, rather associated with the bubble as it passes through the bed. Gas outside the limit of penetration just passes round that entity. The solid lines are the particle flows. So that did explain why, this theory has been used to explain why you do get bypassing and also explain mass transfer in fluidized beds. And sort of just leaping ahead a little bit, it has stood the test of time and scale. And very early on in my career, I was fortunate enough to go on a consulting trip with John to look at oxychlorination reactors. And we were able to apply this theory, and it fitted quite nicely with the problems that ICI actually were getting with that. But also we find, we run reactors just a few millimetres, sometimes centimetres in diameter in the lab. It applies equally to that. And the reason I raised this example in this context is that most of this actually for single phase would have been in the Part 2 course. But of course, John brought some critical insight to this that made all the difference. So the interlink between teaching and research, I think, is proved or tested by this example. He was also able to show from this that the flow through the bubble, the diametral area of the bubble is 3 times that through an equivalent area of particular phase. Again, an important concept. So, what did he have to say about recruitment and collaboration? The department had a long tradition of recruiting academic staff with a wide variety of backgrounds, not necessarily chemical engineers. And I think that CEB has continued to do that, and it is to the good of CEB for that to happen. But it is interesting in his 2020 paper that he added a little rider, the colouring is mine, but there has to be a willingness to learn a new trade and teach it effectively. And so my take on this is that the ability of CEB to lead on new technology and critical challenges does depend on a wide and relevant disciplinary background in its academic staff. And I'm afraid I'm slightly old-fashioned now, but I do think it's vital that new recruits have an expectation and a buy-in of being part of both fields. That, for me, seems fundamental. but I will acknowledge that this is becoming increasingly a difficult issue when recruiting top researchers. We can discuss this offline, I think, because it's a very thorny problem. But I also think that there has to be a willingness to, if you look at some of the research problems that are facing us, there has to be a willingness, I think, to come together in multidisciplinary teams to tackle some of those huge external challenges that we're faced with, and also, of course, the opportunities. Because I think fresh minds are important on all sorts of problems, I think the trend for diversity is a critical one. So, John, in his 1995 paper, listed his sources of useful research problems and new ideas. And as we've seen, actually, John did do a lot of technical consulting, particularly for ICI, but obviously for others as well. And having done a lot of technical consulting myself, it is a source of interesting problems and ideas to deal with. But pretty close to the top of the list was informal contacts in the department over tea and coffee. And it was a rare day indeed if John were in the department not to see him both morning and afternoon talking to people in the tea room. John also, of course, did actually quite a lot of supervising of undergraduates, as many of you will know. And as those graduates went into industry and rose to particular positions, he developed quite an extensive network of contacts. And many of them would come back and talk to John about particular problems. So that sort of informal network also paid dividends. We have the usual sort of fodder, read the publications if you can, and go to conferences. But that was further down the list. Student teaching also gave him some insights, but pretty much down at the bottom was sort of these big set-piece committee reports by sort of big bodies. So he was very dubious about that sort of planned research. So what does it say about how we should be working? Well, I'm afraid, and I agree with this, that I don't believe that hybrid working from home, Zoom, or even these set-piece meetings that you have with companies, they just do not serve us well. It's those informal contacts that we just have to preserve. So I think CB has been quite good at this, but I think there's more to do. And I think we will need to be mindful of these different working patterns about how we constantly encourage informal contacts and conversations. And let's face it, with this building, we've certainly got the architecture to allow that. I really love this one, since it's sort of a bit closer to some of the stuff I do. So John commented on how to manage a department. And so then as now, beloved of HR people are these sort of organograms. The head of department sets the direction, and then from high he hands down instructions to the lecturers, and they hand down instructions to the research students who then carry it out. And they might actually also, further down the pecking order, with the laboratory staff, which is a terrible thing to do. But this is beloved of HR. John actually saw the research effort more as a sort of rolling wheel, and the head of department had to keep this wheel rolling. He saw obviously the initiation of research was the lecturers in those days, and they obviously worked very closely with the various constituencies in an equal way with the other constituencies in the department. And what was the role of the head of department? Well, the role of the head of department was a sort of tyre. And the tyre basically absorbed the shocks in the road, put there by the government, largely. So research assessment is the forerunner of REF. And of course, in 1995, there was a sort of furore about dual funding support transfer, which I'm not going to go into. So I thought to myself, how would this change today? Well, I think the first thing is that the head of department has a much bigger constituency than he actually has to worry about. He even has to worry about the fact that some of the academics will be on a traditional academic pathway. Some of them may well be on a teaching pathway. So there are all of these people, and of course, because there are so many needs for reporting and so on, we have more professional staff to look after finance and HR. Completely important, but equally, but I would say also equally important to the running of the department. What I think all this does is basically means to say that the wheel actually, without anything else happening, is going uphill. So the head of department is much harder. We still have the shocks in the road, so we still have to worry about REF. And then we have other interesting government interventions, such as the furore over Brexit and EU funding, which affects whether academics really want to stay in the UK. And then, of course, we have accreditation and other shocks in the road. So those are sort of the external ones. But even worse is that there is a complete hurricane of university initiatives coming down, blowing straight at this wheel. And I am, as head of school, I'm intimately involved with actually quite a few of these, and I could talk for the rest of the day on it. But these are big things, and particularly this thing, enhanced financial transparency, which means to say you see exactly the costs of each of your operations. The head of department is expected to understand the data and to, in a sense, set the strategy in response to that. So that is a really big thing. You might say, well, what is the school doing in this? Well, I think we possibly act a little bit as a windshield, so we bat back some of the more ridiculous propositions coming from the centre. And I hope we lend a bit of puncture resistance to the wheel. But anyway, that's my view of it, discussed. So what about the future? But I do think this is important. So I think at present, being head of department largely precludes, I think, substantial involvement with research and teaching. And having done it, I do think it is one of the most difficult jobs in the university. Knowing other heads of schools, they believe the same. It's full-time management. And actually, after you've been totally exhausted for 5 years, what then happens? So I think we ought to be thinking about a radical rethink of this. I think we probably need to be thinking about proper succession planning. I do think planned load sharing with deputy heads of department is important. And I think we need to make dedicated and sacrosanct time available for the head of department actually to do some research and maybe some teaching. They've taken this to extreme in our neighbours next door in materials science, where they've actually got a triumvirate. Actually, it's probably not right, because the three heads are there's a mixture of men and women. But I can't get, my Latin isn't good enough. But basically, they're sharing the headship amongst the three equally. So this is a grand experiment, and it'll be interesting to see what comes out of that. So we'll keep tabs on that. So the final thing I wanted to say, and I'm probably speaking for too long now, is John was always supportive of new science and technology. We've seen that. I think he was one of the, certainly when I was a student, I think he was one of the first people to have online data logging, and I remember the bubble size work in the labs. Of course, he was instrumental, along with Chris here, at bringing biotechnology into the fold. Food technology, I think, he was also instrumental in, and of course, we've heard from Lynn on the magnetic resonance imaging story. And I think it's great to see that I think this is a continuing tradition in CB. Lynn's gone through all of this, so she's taken my talk away here. But the interesting thing about this was actually, I think this started with a Friday afternoon experiment by the good Professor Fennell, who decided that he might put a fluidized bed inside a magnet just to see what happened. And in later versions of this, we saw these interesting patterns that Lynn has spoken about. And this isn't noise in here. These are all related to bubble coalescence events. And as Lynn has said, what we were able subsequently to show is speed before, during and after a coalescence event. We were able to verify John's work on bubble rise velocity, also his work on bubble sizes, and we were also later able to image the gas. And I think we almost got to the stage where we were able to show that, I said that the flow through the bubble is 3 times the particulate phase. We got close to showing that holds as well. So this really did back up John's original theory. So I put it in really because it's a sort of nice closure on some of the early fluidization work. So what about the future? So I must move a bit faster now. So I can't talk about all of these. I'm just going to say a couple of words about the first two, but we also need to be aware, and I think that the department is, that AI, ML, data science and so on is continuing at rapidly apace. And of course we've got quantum computing coming along. And of course we're playing to an evolving industry, and I think the employment emphasis for undergrads in the future will be a shift to multidisciplinary teams. That isn't multidisciplinary in the engineering field, it's multidisciplinary across fields in specialist sectors, and I think way outside the traditional ones. But this is the sort of grimmest slide of the afternoon. This is energy and transition, so this is extracted from the BP Statistical Review of World Energy. And this is basically world consumption of energy and divided by, sorry, I can't read it from here, so I guess you guys can't read it, but basically what it's saying is that our energy use is inexorably increasing, and both coal, gas, and oil are still increasing. And what you also do, if you look at these, is that the penetration by renewables is nowhere near enough to offset that increase. And if you look at the CO2 concentration from just before I came back to the department to now, it's just rising linearly. There isn't even a blip, really, a noticeable blip around the COVID years. So despite all the discussion, this doesn't look anywhere close to an energy transition, and something big has to be done about this, otherwise we're just frying the earth. So, you could say, well, rollout development of renewables at an unprecedented scale is needed, and of course the department would have a key part in this. But of course we're seeing now the issues of energy affordability. Energy, of course, is a weapon. And of course you might do the renewable stuff, but have we got the elements to do it? So sort of grim a bit for an afternoon. But the biotech story, of course, is a much happier story. The department has long been in this sort of area, but with, I think, increasing emphasis, I think, for biotech, health, and medicine. And certainly in my position, I'm able to talk to the head of the School of Clinical Medicine, and they are very enthusiastic about collaborations with engineers in all their form. But there are many experts in here who will know a lot more about this, but basically it's much easier now to edit genes, and so that means to say there are all sorts of new medicines and new ways of treating disease, which sort of tend to be more individualistic. There are affordable genome analyses, and so you can individualize medicines. But I think the big one that we need to be taking care of is that clearly systems biology as a computational tool for understanding how biology works is important, I think, now to the engineer, and how we apply those systems to bring about new processes in medicine is really important. And of course, somehow we need to get information from all those vast data sets that are generated. It goes without saying that all of the work that has been done and will continue to be done on sensors, devices, synthetic materials and so on will be important. And of course the engineer needs to be worried about the ethical dimensions of some of these things, such as genome analysis. So I'm almost there now. So what would be some features of a future curriculum? I think we have to preserve this sort of core. This isn't exhaustive, but I think that has to be there. I could see some rationalisation of some of the traditional content, such as some of the distillation stuff. But I do think the big question for us is how do we actually quantify biology and get it sort of embedded in the course in the same way that we embed, say, chemical thermodynamics in the course. I think that's a real challenge still, because I think the engineer of the future needs to ask himself or herself, how do you design the biology plus the process optimally and quantitatively? And so what I'm saying there, I'm not saying that it's the same as thermodynamics, but could we treat it in the same way that we strip down to the essentials of thermo? I do think that AI, data science, tools and techniques, I think they have to thread through all the years of the course because our graduates will be faced with those. And I think in a world which is basically beset with quick-fire judgments powered by social media, that includes the centre of this university to some extent, we need graduates that can think about complex interacting systems. So this goes beyond just the process system, but how that system fits within another system. And to some extent, this is being pioneered in the Whittle. Fortunately, we've got EVA, in fact, is collaborating with the Whittle on the interacting systems around zero carbon aviation, where there isn't just one story, of course, to decarbonise it. And by soft, I mean basically these are systems that have human judgments in as well. Anyway, that's my view, but based on JFD's scepticism about pundits, treat it with care, because I'm sure it'd be wrong. So what are my conclusions? Well, I think there's a highly promising future for CB. The discipline, I think, remains very relevant to solving our most pressing problems. But the future potential and impact of CB, of course, is about its people and about how they think and interact, about the depth of their research vision, and also, I think, in how they teach succeeding generations. I think the guiding principles, I won't go through these again, but I think the guiding principles from John hold good. But I think we have to note that the academic environment has altered substantially, and so thinking about how John's what seem to be very simple principles apply in the more complicated world of academia, I think takes some more debate. So that's all I'd like to say. I'm sorry I'm a little bit over time, but thank you.
Thank you so much, John. We started later, and I'm responsible for keeping, so I want to make my speech short. Our next speaker is a little different than we had it's different person than we had in the program. We needed to have a change because another person was sick. So nevertheless, we're going to have a great presentation from Professor Gabi Kamiński-Szirle, who's a professor in molecular biotechnology in our department. Gabi did her PhD in Lund in Sweden in medicine. I was very surprised discovering that today, Gabi. It's amazing, also shift from medicine to now being a head of molecular neuroscience group in our department. And Gabi's research combines unique set of engineering, biology, biotechnology skills in one research. I personally consider this amazing. I have no idea how you're managing so many areas in one group. And Gabi is representing with her talk today our area from the department in the healthcare science. We're going to have later talk on energy and final one on sustainability. So healthcare is for you, Gabi.
Thank you so much, Eva. That's an amazing introduction. I have to live up to that now. So yes, I am representing the health-related work that is going on at this department. And today I will be talking to you about combining optical and engineering approaches for the study of neurodegeneration. So I'm mainly interested in studying Alzheimer's disease. And the reason is quite obvious because there's so many people suffering worldwide from this devastating disease. And the main risk factor is age. And in an aging population, obviously this is scary for all of us because the likelihood that we will develop this kind of disease the older we get is increasingly likely. So the costs currently are bigger than the costs for cancer, and that is because obviously all the people looking after these elderly people and taking care of them obviously it all costs a lot of money. So some of the hallmarks of this disease is that there is a loss of brain cells or neurons, and this happens in a very particular neuron region inside the brain, and these neuronal cells are important for memory function. So that's why when you meet an Alzheimer's patient, you will know that they will struggle with memorizing things. And the really worrying bit is there is no treatment currently available. So I know I'm probably primarily talking to chemical engineers here, so I'll give you some illustration of how a brain, to me, might look like, or does look like. So if you see here what I call normal is a non-Alzheimer's brain that is quite has a certain size and
we call the ones on the normal side are the happy neurons, whereas the one on the unhealthy or the diseased side, the Alzheimer's disease side, you can see that the brain has shrunk significantly. It's much smaller. This is due to the loss of brain cells, and the neurons are also less happy. And they are less happy because there are two known proteins called amyloid beta, which is a small protein, and tau, the other protein. They form these clumps inside the brain. And what you can see here, what I've drawn here, these are called, these clumps are known as so-called amyloid plaques, and they would be found in the extracellular space. And then today I will be mainly talking about the protein called tau, which also forms these clumps, but it's forming these clumps inside the neuron, so inside the brain cell. And that we will hear more about that, how this is really affecting normal neuronal health. Okay, so what is our approach? I was talking about engineering approaches. So we are interested in why and how these neurons die in disease. So we know that these neurons, they lose their ability to communicate with each other. And that obviously is very, very important, for memory and for everything, all the activities we do. They need to be able to communicate with each other. And we are working together very closely with engineers, and we have developed so-called microelectrode arrays. And these microelectrode arrays, they can measure neuronal signals. That's the way neurons communicate with each other. But the current devices that are currently on the market, they are not really usable to visualize at the same time the molecules that can cause the disease. So what we're trying to address here, so we want to see these molecules as they go inside the cells, how they directly can cause the disease. And obviously once you can see how this is happening, can you then add a drug which is stopping or blocking this? So the vision here has been to design these new transparent devices and then using a machine learning based approach to classify these neurons in this kind of network. And what do I mean by that? Obviously, every neuron has a very particular way its signal shows up. And so when you measure these, what is called action potential, and I will tell you a little bit more what an action potential is in a minute, but that's the way they communicate with each other. Each neuron has a characteristic signature, the way it's doing it. And so we, using these machine learning approaches, we can now try to understand which type of neuron might be more affected or less affected by the protein that is causing the disease. And for that we use these machine learning approaches. And I will talk more about that as I go through the talk. And obviously the application is, so we want to design a platform on which we can study optically and also electronically how these individual proteins are causing disease, to really get to a molecular understanding of how disease is caused in these patients. Okay, so this is the devices we have fabricated. These are two students that are in the group who did this work, and they were co-supervised by people at the engineering department. So we have, this is like a commercial device. So we more or less copied this device, and we used different electrodes, and these electrodes have the advantage of being almost fully transparent. And one type of electrode is called P.PSS. This is a polymer, and this was done in collaboration with Professor George Maliaris at the engineering department. And we made these microelectrode arrays, and they have a really high transparency. And if you look at the impedance characteristics, their signal-to-noise ratio, because of the lower impedance compared to commercial devices, is significantly improved. Then we also fabricated, this was another student in the group, together also with people from the engineering department, we fabricated graphene-based microelectrode arrays. And the graphene has the big advantage here that it's almost 100% transparent. So it's because it's one atom layer of graphene, it's really, you can see through it, and you can do sort of high resolution imaging through that. And the impedance is between the commercial and the other device. Okay, these were the three devices, and now we wanted to test neuronal signaling in these cells. So just very, very briefly, what is neuronal signaling? I was talking about the so-called action potential. And you see one of these action potentials here. This is this curve. And this is happening due to a membrane depolarization. You can see that under resting conditions, you have the membrane potential is negative here. As you can see here, in that on that line is about -70 millivolts. And then as the ions move across the membrane of the neuron, you can see that there is a significant depolarization happening, and this leads to the increase in the voltage. And then you have, after that, you will have the turnaround. So the sodium ions are going to go back in, and the potassium ions going to move back out again. And you see the repolarization is happening, and then it all flattens up again. And you can measure this in two ways. You can measure this by what is the traditional technique, by patch clamping and going directly inside the neuron to measure it using sort of intracellular electrodes. But you can also measure it in the extracellular space, and this is referred to as the electrical field potential. And this is what we are measuring in these microelectrode arrays. Okay, so how does a result look like in practice? So what you can see here is a typical sort of a recording that you get. If you look at these larger spikes, these are the individual action potential. And you can see here this neuron is firing quite nicely. And to confirm that this is a real sort of action potential, we measured calcium entry into the cells at the same time. Because after every action potential, there is also calcium coming into the cells. So we can do sort of correlate the signal optically using a fluorescent-based calcium sensor, and obviously by measuring the voltage change over time as well. Okay, so what we can now do, we can use our transparent devices we grow the neurons on these transparent devices, and then we add fluorescently labeled protein to the cells. So this is the protein tau that I've said before at the beginning that can cause Alzheimer's disease. And now we can, because the tau is now fluorescently labeled, it enters the cells and we can monitor exactly where inside the cell the tau is. And at the same time, we can see what it does to neuronal signaling. So, as said here, this is an image through these graphene electrodes. You can see the neurons beautifully. You can see all the individual structures. You can see the network and everything. And we can see clearly where the protein is going inside the cell. So when we did the measurement, so what we discovered was that this Alzheimer's disease protein reduces the neuronal firing capacity in these neurons. And this was really the first time this was shown. So what is quite interesting, so if you look at the signal here, so you have your typical a response here, your action potential. And in particular, when we added the tau while stimulating the neurons prior to that, we could show that there was more of the protein taken up due to the stimulation, which led to a complete silencing of the signal. That means these neurons are now not able to communicate with each other anymore. Obviously, what we are now wanting to address is what type of neuron is dying in our system. Is it, for example, you have different neurons that are called excitatory neurons or inhibitory neurons, and it's been shown that inhibitory neurons might be more vulnerable to stress, especially during aging. And so, as I was saying or alluding to at the beginning, is that we can now use machine learning-based approaches, and we can, looking at a unsupervised, we're using an unsupervised algorithm here to classify the neurons into excitatory or inhibitory neurons. And you can see by the form of the action potential, as it was shown here, we can see that they clearly group into two classes. One of them is excitatory, that's class 0, and the other of them is inhibitory. And you can clearly distinguish the two. And then we can go back, because we have these electrode numbered in these devices. We can then go back and look at, do a staining of the neurons inside the cell culture dish. And it might be a bit too bright, but we might potentially see that the electrodes that I highlighted here are the ones that show that there is an inhibitory neuron sitting, and these have a green neuron sitting very close to it, which is the marker for inhibitory neurons. So this is really a proof, like a ground truth proof, that the algorithm that we have developed is really working and is recognizing the two different populations. So all of this wouldn't have been possible without the help of these amazing people, and also the doctorate training centers that we have access to. So one is the Sensor CDT, which is run in-house, and Sagnik was that year's Sensor champion who joined the group and worked with George as well very closely on the PWSS devices. And then Marius in the middle, he's a machine learning person. He came through the MPhil in biotechnology, which I'm running at the department, and the graphene CDT. So thank you for your attention, and yeah, it's been a pleasure. Thanks.
her work also is multidisciplinary. She combines research on catalysis, reaction engineering, separation. Laura's good and also very productive in efficient production of nanoparticles, microfluidic reactors, and I think her group shows how these areas can be brought towards industry, and I hope she's going to show you more in her presentation.
Thank you, Eva. I would like to start saying thank you very much for all our guests today for joining the department to celebrate the life and the work of Professor John Davidson. I believe that he was the only professor for a while and well deserved. So it is thanks to his work, I think, and the work of those of his generation that the 20th century saw a transformation in our society, in our lifestyle, and it was enabled by fossil fuels. And fossil fuels have the versatility, and they have the way to meet the demands of our society on electricity, on transport, on heating, powering, chemical processes, providing the feedstocks for chemical processes. And I think that we should be grateful for this because, as I say, it is what enables our lifestyle. But we cannot be satisfied because we now understand without any questions that those CO2 emissions, methane emissions, you can even see them from satellite images, NOx emissions, have created a climate crisis. And Jan mentioned that renewable energy has been disrupted this way of transforming energy, but actually is a tiny little bit, and it only meets our electricity demands. And right now, I think that the UK should be proud that we meet 80% of our electricity demands using renewable energy. And I will say that that is the easy part. Now we need to act for the rest. So this department is fully committed to provide the fundamental science and technology in exactly the same way that it was committed 60 and 70 years ago to transform society, in particular to transform the way that we produce and we use energy, and hopefully to achieve net zero by 2050. I would like to make a point about what is the scale of the challenge, because it's just, I think that this is exactly the same graph that John used. This is a grand challenge. We're all aware of this. The world consumes around 15.8 terawatts of energy, primary energy, and we have around 15% is based on renewable energy at the moment, and that is only if you consider traditional biomass. So we have a long, long way to go. The International Energy Agency has a roadmap, has published a roadmap to say what we need to do if we want to achieve net zero by 2050. These are the targets for 2030, which are only 7 to 8 years from now. We need to multiply by 4 times the solar and wind capacity, which I believe we have the technology and is feasible, but we need to multiply by more than 200 times our electrolyzer capacity, and I'm not sure that that is completely feasible by now. We also need to think about many things. I'm not going to touch on politics or other aspects, but we need to think about whether we have the capacity. Anyway, this is my personal vision of the future, and I'm going to give you just a taste on what we are doing as a department, not only based on my own research, but also I'm going to touch a little bit on what others are doing, on how we contribute to this. I say that this is my vision because there are different versions, and I think that they are not exclusive. I think that they are all needed, but in my opinion, one of the issues, one of the problems of renewable energy compared to fossil fuels is that they are intermittent and very difficult to store. We accept that. And I am a great believer that storage of energy in chemical bonds, in exactly the same way that fossil fuels do, is part of the solution. And I'm going to present a little bit of our work on ammonia. But as I say, I'm going to try to give you also a little bit more ideas of what we are doing in the department. And there are two players. One is ammonia, as I say. And the other one is perovskites. And this is the world-leading research done by Professor Sam Stranks, who unfortunately cannot be here today to present his work. But he is a world leader on the development of halide perovskites, which have this particular crystallized structure, an ABX3 crystal structure. And you can see here that if you change the halide in cesium-lead halide perovskites, you change completely the way that they interact with light. So they are very interesting materials. What they are developing is a way of understanding from a photophysics, a chemical, and a material, how these materials behave and how they can be used for PV panels. Here in this graph, I show what is the efficiency that you can get with silicon, the conventional photovoltaics, and the ones that the development of these perovskite materials in the last 10 years. It's quite amazing that these materials were discovered only 10, 12 years ago. And then in this short period of time, they've been able to compete in terms of efficiency with the silicon PVs. I have to be fair here. I say that there is a lot of research interest in these materials, and then probably they push this area of research. And also to say that this is driven by a need of capturing solar energy in a more efficient way. The efficiency limit, I've been told by some, is very similar to silicon. So I asked him, why are they so interesting? So I got a short lecture by him, and he very nicely explained to me that it's because of this variety of chemical structures that you can have what is called tandem photovoltaics. So you can combine in this kind of sandwich configurations different materials, some of them able to capture the UV and the visible wavelength of the solar spectrum, and then combine them with other perovskite materials able to capture the red and the near infrared spectrum of the solar. And more importantly, well, you can go above those practical efficiencies that the silicon PVs are not able to, but most importantly, they are very cheap. They are a fraction of the cost of the silicon, and then their greenhouse gas emission factor is also lower. So there is a range of activities in this area in the department and across the university, from understanding the materials, understanding the defects, to making the devices. And here you can see on the right-hand side how using roll-to-roll technology, they are able to print very, very thin films of these perovskite materials. This is a material that is making very fast impact in a very short period of time. And Sam is a co-founder of this company based on the MIT, that they are trying to commercialize these high-power, lightweight solar panels. Okay, I'm going to move now into the second key player in my presentation, which is ammonia. You might notice that I have replaced fossil fuels by ammonia here. And there are a few reasons why I've done that. And the first one is because if you look at the chemical molecule, it's very similar to methane. Exactly the same. Both molecules store energy and release energy by breaking the nitrogen-hydrogen or the carbon-hydrogen bonds. So it's exactly the same. The big difference is the atom in the middle. Methane produces, obviously, CO2 when you combust it. Ammonia doesn't. I'm more than happy, and I'm sure that I'm going to get a question about NOx emissions, but I'll keep it to you later. The good things about ammonia is they have a very high energy density, comparable to those of fossil fuels, much higher than hydrogen at 700 bars. And it contains itself more hydrogen than pure hydrogen, okay, by weight. But there are two more things that are quite important. The first one is that the infrastructure is already available. And this is a map that shows how ammonia is being transported around the world at the moment. There are countries like Russia and the United States that they have thousands of kilometers of ammonia pipes connecting different states and regions in the different countries. So the infrastructure is already available. And the other important aspect, in my opinion, is that they are as versatile as fossil fuels. So that is why I was a bit bold and I replaced ammonia by fossil fuels in my overall vision of the future. So you can take ammonia, you can crack it, you can produce hydrogen. So it can be hydrogen storage vector. But there is a lot of research about how to use ammonia directly in fuel cells. You can combust it in a similar way that we combust hydrocarbons at the moment. I say that this is a molecule that is fundamental to our society, feeds 50% of the population. We know how to make it, we know how to transport it, and we make it through this very, very famous process, the Haber-Bosch process, and it consumes around 2% of the global energy, which is similar to the consumption of the aviation industry, if you want to put things into context. So as a result, it produces around 2% of all the CO2 emissions just for its use as a fertilizer. And this is a process that has been optimized over the last century and is actually reaching its thermodynamic equilibrium. But in my opinion, this is a false optimization. It is a false optimization because it's optimized to extract hydrogen from fossil fuels using steam reforming to produce steam to drive the rest of the process. So it is a false optimization. And I remember when I presented my vision at the beginning, when I joined the department, Professor Davidson said, we have worked so hard to get this process as it is, and now you want to change it. And I didn't have an answer at that point because I didn't know how to do it. But now we are moving into the right direction. So green ammonia is very, very similar concept, but in this case we are producing hydrogen using a renewable energy split in the water molecule. And you might see a big difference between this slide and the previous one, and is that in the previous one you produce heat in the steam reforming of methane to drive the rest of the process. That is not possible anymore here, but it creates opportunities to get that new optimization that I was mentioning. So this is a very, very quick summary of what we are doing in this department. This is the conventional Haber-Bosch process. I believe that doesn't need any explanation to most of the people in this room. But it is, if you look at the process from a holistic point of view, you might realize that the whole process is limited by using condensation to separate ammonia. That means that you need to work at high pressures, you need to work at high temperatures to also overcome the thermodynamics. But if you replace the condenser with absorption, then you open the door to mild pressure operation immediately. So the way that you can separate ammonia at lower partial pressures is feasible. What we are doing now is to integrate everything. So we are integrating the reaction and the separation into a single vessel. So that Haber-Bosch loop is not a loop anymore. It is a single vessel process, and the most important thing, it can ramp production up and down from 0 to 100% without reaching any safety issues to cope with the intermittencies of the renewable energy. Okay, a very brief summary of how we achieve this is by developing new catalysts, new materials to able to absorb ammonia at high temperatures. So this is a new catalyst, a ruthenium-based catalyst. We are now working on ion-based catalysts. Obviously, there is a difference of price on there, and it's feasible to reach not only high rates of reaction, but also be able to approach the equilibrium. By combining the catalyst with an absorbent, we are able to get single pass conversions above the thermodynamic equilibrium. So I normally say to students, there's nothing that you can do against thermodynamics unless you are an engineer that really understands thermodynamics. And therefore, you can integrate processes and get conversions above equilibrium. I'm more than happy to discuss these results with whoever is interested. We have also developed new ways of integrating heat, because if you are thinking about a new chemical industry that is going to operate in an intermittent manner, then all the heat integration processes are not valid anymore. We need to think about new ways of heat integration. And also, as part of this, I call it chemical revolution, we might not be able to enjoy the economy of scale anymore in the way that we do it at the moment. So we might want to produce ammonia in a distributed manner. Therefore, we need new processes that can compete with the conventional Haber-Bosch. Anyway, I think probably I gave you an idea that one of the problems of the renewable energy is that it's intermittent, it is distributed around the world. How are we going to run the chemical industry in this way? Well, hydrogen production can cope with those intermittencies. It is scalable. The question is, how are we going to electrify the chemical industry? Is it going to be intermittent? I think that the answer is yes. Is it going to be distributed? In my opinion, the answer is partially yes. But there is a lot of new development to do here. So I say also to the students that this is an extremely exciting time for chemical engineers, because we need to change the way that we do things, and we need to build on what it has been done before. This research is supported by other groups, obviously, and I'm going to touch only on what the magnetic resonance group does. And they, as Lynn mentioned this morning, they're able now to visualize what happens inside these chemical reactors. And I think that this is critical if we want to modify the processes. So this is a Fischer-Tropsch reactor or setup, and they introduce the reactor inside the magnet, and that allows them to visualize flows, visualize product distribution within the catalytic bed. I think that this will be critical if we want to run these processes in an intermittent manner. I'm not going to mention at all what Eva and John are doing, because Eva is going to provide a summary later today. Anyway, the conclusion is exactly the same that I said before, is this department is fully committed to contribute with fundamental and engineering principles to transform the way that we use and we consume energy in the future. So with that, acknowledges to my group and to the different funder agencies, and thank you very much to you for your attention.
Thank you, Laura. We should be starting a break, which is going to be 10 minutes shorter than expected, but let's allow for one quick question from Peter. Quick question, right?
Okay, I ran the ICI research on the ammonia process. I'm very interested in this. I did it for about 10 years. There are all sorts of problems with the absorption-desorption loops you described.
But the thing I didn't quite understand is there's a very easy way of sorting out the hydrogen intermittency problem.
Which
That is to have a low-cost way of storing liquid hydrogen, because that does much better than the ammonia.
Yeah.
So perhaps you could just say.
Yeah. I can really mention on that because we are doing techno-economic analysis, and all our studies, which we have published a couple of years ago, shows that storing hydrogen kills the economics of the process. But new technologies will hopefully appear. But at the moment, and we are talking to many companies around the world, from India to States, hydrogen storage for 10 hours of the day only accounts for 25 to 30% of the total cost of ammonia. So at the moment, it kills the economics.
I think it depends on the cost of the hydrogen storage.
Absolutely.
If you
Yeah,
can
but
get that,
correct.
then it's,
Yeah, certainly.
Thank you so much. Let's go into a coffee and then we'll start promptly. I did this make my speech shorter.
And just finally, we have the Deputy President of the ICME, Nigel Hurst, here to, I think he's going to become the President.
I will be President from June next year. So
the President Incumbent.
President Incumbent, yes.
From ICME to say a few words about the ICME and closing remarks.
Okay, thank you. Well, it's lovely to see everyone here. And I'm very aware I'm the only thing standing between you and the drinks. So maybe I ought to put myself between you and the door in order to make you wait. I've never been in this lovely building before, but what a great thing it is. And if we can, how do I change the slide? There we are. I noticed some of the memorabilia has made its way from Pembroke Street. And that is the 1977 year group photograph, which I'll show you for three reasons. One is, oops, sorry. Oh, we've lost the whole thing there. Right, just let me go back. Oh, here we go. I should have had instructions on this. Where's the laser pointer? Oh, there we are. One is to show that I once had hair. That's me now. The second is that it actually shows the images of 5 ICME presidents. Obviously, John Perkins, Sir David, a very young Stephen Richardson, Professor Stephen Richardson of Imperial, and me on the end. And for some reason, Des King's not on it. Otherwise, it would have been 6. The third reason I show you the photograph is that in 1977 there were only 13 people in the undergraduate class, and the reason for that was that after the oil crisis in 1974 there was no future in chemical engineering. In the early 90s, when John retired, he held a wonderful, an event a bit like this in the Babbage, where the great and the good came to give lectures in his honour. And it was followed by a splendid dinner in Trinity. Those were the good old days. But the lecture I still remember today, was given by Octave Levenspiel, the chemical reactor man. And his tribute to John was this: the genius of John Davidson was not that he asked the questions no one else did. He asked the questions no one else even thought of. And he illustrated it with his now famous discussion about dinosaurs. And the question everyone asks is, well, why did they become extinct? And Levenspiel said the right question is, how did they exist in the first place? And by some simple, what I call Fermi approximations, he showed that the pterosaur couldn't actually fly in an atmosphere like we have today. So the thing would have had to have glided down, swooped on its prey, and then trudged its way back up the top of the hill. And that led him to the conclusion that the atmosphere in prehistoric times must have been high in CO2 and at higher pressure. But those are his original cartoons. You can find all this on the internet. It's very interesting. So, what is chemical engineering? Fill in the blank. We battle the negative connotation of the word chemical. The general public associate chemicals with heavy industrial chemicals and their negative effects. But in many ways, every substance is a chemical. And it underlines the universality of the discipline. I never thought I'd meet a professor of bioelectronics in a chemical engineering department. It shows how times have changed. But the iChemie is a charity, and as such, it has official objects, which I'm going to come back to in a minute. But we're celebrating 100 years of the iChemie. It was formed by a meeting of the great and the good at the Hotel Cecil in London in 1922. And to celebrate this, all this was done under the pandemic, of course. We pulled together a team of willing volunteers, volunteer members and friends to create a digital archive which shows the world of chemical engineering to people who have an interest in it. I don't know if I can click on this. Don't know how to do it. All right, it doesn't work. Never mind. I'd encourage you to look at that. It's we took the UN Sustainable Development Goals and reworked them into things which meant 9 topics, which meant something to chemical engineers. We spent 25% of the effort on the past, 25% on the present, and 50% trying to look into the future. And there's video discussions with students and people from all over the iChemie world discussing their view of chemical engineering into the future. The charitable object of the institution is to serve society. And we produced a film, a series of films with ITN called Serving Society. And this is intended for consumption by the general public, really to look at what the positive benefit of chemical engineering is and has been over the years. So going back to the UN Sustainable Development Goals, there they are. There are 17 of them. If you go into most iChemie member or partner companies, you'll find that these form some part of their mission statement. They're very powerful. What we did as a result of this project, we divided them into 3 groups. The one on the left here, there are 5 things, the 5 things you see there, which we believe that only chemical engineers can take the leadership of. The 6-1 partnership, I'll come back to in a minute, we can make a contribution to the others, but only chemical engineers can take the lead in this. And the challenge for the iChemie is how we mobilise members, university departments, industrial partners into making this happen. And the thrust of my presidential year will be to try to elevate the influence of chemical engineering onto a higher level, if you like, with governments, the civil service to bring together the expertise which we've seen so well demonstrated in this room today to make a bigger contribution to the direction which the world takes. In November, we're going to have 2 volunteer celebration events with 2 lectures, one in Manchester, one at Imperial in London, about process safety and life cycle analysis, which, in my opinion, are the 2 gifts of chemical engineering chemical engineering has made to society, which even a non-expert can say is a positive benefit. I said the ICME has objects. Past President Richard Darton tried very hard some years ago to write out in great detail what chemical engineering was. The trouble is, the more you try to be specific, the more people come up with new areas of interest which are incorporated into it. And so the last thought I want to leave you with is this, that the object for which the institution is constituted is to serve society by fostering and promoting the art and science of sustainable chemical engineering. And I think that's something which no one could argue with. It's something which is easy to remember, and it can run through the ethical and sustainable life of engineers, whether they're academics, whether they're in industry, whether you're retired, whether you're interested in getting into chemical engineering. It is a clear object for the future. It will put us at the lead of all the engineering professions, which is where I believe John would have liked us to be. Thank you. Happy to take questions if you want to be spared the drink, but I'm happy to retire.
I don't think anybody is showing signs of being
good.
spared a drink. No. So thank you very much,
thank you.
Nigel. I'd like a couple of thanks. Firstly, a thank you to all the speakers. We've clearly lots of interesting, some great thoughts about John, some common themes coming through about what an inspirational, valuable person he was to the department, but also some interesting thoughts about where we're going in the future. So just a quick thank you to all the other speakers from today. I would also like to help all those people wearing the heart valve T-shirts, all the helpers that have been showing you around, that have been getting things organised in the background. So without them, it would have been it wouldn't have happened in the same smooth way as it has. So thank you to all those. And finally, just a particular thanks to Roisin, who's organised this and hasn't had a thank you yet. So it's been a great day. There's obviously lots going on behind the scenes, which has been getting to be able to arrange this. And then you get 3 people pulling out in the last week because of COVID and so on. Shows we're not completely over COVID, but the fact is today's gone really well despite that, or even possibly because of. So thank you very much to everyone. And now I think hopefully there are drinks outside, so you can go and have a tea and chat as you've been doing before, or indeed a wine or beer.